Welcome to Web Application Security. In this course, you will build a strong foundation in web application security, starting with an in-depth understanding of common vulnerabilities and their impacts. Through practical examples and techniques, you'll develop the skills to identify, mitigate, and prevent security threats, preparing you to tackle real-world challenges with confidence. We will begin by exploring common vulnerabilities in web applications, including SQL injection, XSS, and CSRF. You'll analyze their impacts on application security and explore real-world examples to understand how these vulnerabilities are exploited and mitigated. Next, we will examine secure coding practices that strengthen application security. Topics include input validation techniques, output encoding, and data sanitization to ensure the safe handling of user inputs. You will also identify best practices for authentication, authorization, and secure data storage and transmission. Next, you will harness the power of Microsoft Copilot to enhance application security. Learn how to use Copilot to detect vulnerabilities in code, fix security issues, and implement secure coding practices. You'll also apply Copilot in a comprehensive review process to evaluate your ability to build secure web applications. Finally, you will consolidate your skills with a Capstone project, where you'll apply the techniques and tools you learned throughout this course. This hands-on project challenges you to identify vulnerabilities, apply secure coding practices, and implement robust security measures in a realistic scenario. By the end of this course, you'll be equipped to identify and mitigate web application vulnerabilities, implement secure coding practices, and enhance application security using Microsoft Copilot. We're excited to guide you through this journey and empower you to build secure, reliable web applications that withstand real-world threats. Hello, my name is Tyler Morgan, and I am one of your instructors for this course. I've been a developer since 2011 when I started writing my first applications. However, my journey with programming began much earlier. I first tried to learn programming back in 1999 when I was in the 7th grade because I wanted to build a video game. I eagerly picked up books and tried to learn on my own, but I failed miserably at even grasping the basics. The main reason was that I didn't have anyone to guide me and show me what I needed to do. This experience scarred me so much that I didn't attempt programming again until I was in college when I was required to take an introductory programming course. In that course, I finally learned the very basics of programming. It gave me the confidence to believe that programming was something that I could tackle. The problem was that while I understood the syntax of programming, I still didn't know how to turn if statements and for loops into software. It wasn't until I discovered online courses that my abilities as a developer really took off. These courses held my hand a little bit, showing me what I needed to learn and steering me away from topics that were too advanced for my experience level. Thanks to the help of these courses, I began to understand how the web worked, how to build software, and how to turn the things in my imagination into reality. I was so enamored with online learning that I went to work for an online education company, building their alumni network. That work gave me the confidence to break out on my own as a software developer. I started a company called Numerite, where I did cutting-edge web-based visualization work for the federal government and groundbreaking machine learning for university researchers. And I created awesome tools for huge companies. Then a few years ago, I had the opportunity to fulfill my dream of starting a farm. Now you might think farming has very little to do with software engineering, but it's amazing how handy it is. I wrote my own software to manage crop planning, built our website, and integrated with external services to create the functionalities that my customers wanted. I created entire data pipelines to ingest local market data and determine where there were gaps in local agricultural production. I'm sharing all of this with you because learning how to be a developer isn't just for those who want to work for big tech companies. It's an amazing tool for anyone. And with proper guidance, you can learn what took me decades in just a few months. So let's get started.
The learning experience in this course is designed to give you a comprehensive understanding of key concepts through various learning methods. You'll be guided through interactive, engaging materials that help you build practical and theoretical knowledge. Whether you're interested in front-end, back-end, or full-stack development, this program has the tools to support your growth every step of the way. Throughout the course, you'll be introduced to core concepts and key ideas in videos. These videos are designed to help you understand definitions, processes, and essential steps clearly and concisely. You'll get to absorb foundational knowledge, setting the stage for deeper exploration as you move forward. And when you need step-by-step guidance, screencasts will provide you with a detailed practical view. These screencasts will show you exactly what's on the screen and how to work through specific coding tasks. The course also includes readings that reinforce the key ideas presented in the videos. These readings are more than just supplementary material, they're job aids. You can print them out and use them as a reference while working on assignments or activities, helping to apply what you've learned in real-world situations more easily. Small activities are included to help you check your understanding of key ideas. These activities provide quick, interactive opportunities to practice what you've just learned. After completing each activity, you can compare your work with a fully explained example and answer key. This ensures that you always know if your answer is correct. Practical experience doing tasks you would in a job within this field is essential, and that's where guided labs come in. These labs take you through the implementation of different concepts step by step. As you work, you'll receive feedback and helpful hints, ensuring you can get the help you need when you need it. It's the perfect opportunity to practice in a controlled environment while learning by doing. After completing the guided labs, you'll move on to independent projects, or you try it. This is where you'll put your skills to the test, applying what you've learned in the labs. You'll work through real-world problems, cementing your understanding of the course material. The course will culminate in a practical project leveraging Microsoft Copilot that you can use as a portfolio artifact when you begin your job search in this field. As you progress through the program, the portfolio pieces will become stronger and better representations of the authentic experience you've gained. They'll showcase your understanding of code and the ability to implement different concepts from the developer program. This course guides you step by step from understanding concepts through videos and readings to apply them in activities, screencasts, and labs. Each part of the course builds on the last, helping you gain knowledge and authentic experience. By the end, you'll have completed real projects that not only showcase your skills, but can also be included in your portfolio as you start your career. Everything you do here will prepare you for success as a developer. Let's get started.
Throughout this course, you'll complete several guided labs. These labs are meant to give you an opportunity to practice your newly learned skills in an environment where you can get help and feedback as you complete coding challenges. This video will describe how to complete the guided labs in this course. We will explore a guided lab together so that you'll know what to expect when you come to one later in the course. First, let's check the content leading up to a guided lab. This structured content ensures that you have exactly the skills you need to complete the task. In this instance, there is a practical application video that describes in detail how this concept is used in real-world situations. Following this practical application video, you can review a reading that explains the concept in detail so you can go through this content at your own pace. Next, you'll find a video that works through the guided lab itself. This video won't give you all the answers to the guided lab, but it will provide an overview of the upcoming questions and challenges. Lastly, we come to the guided lab itself. The guided lab is a simulated code environment where you can experiment with code and receive hints and feedback in a realistic coding situation. To start, I'll click Start. In this lab, step 1 is an introduction to if-else statements, so I'll click Begin. Below the simulated code environment, I can find the specific instructions for this lab. Declare the variable age as type int. Place your cursor into line 2, type your answer, and select Enter to check your work. Alright, I think I know this one. I'm going to type in INT and hit Enter. Great, I got that correct, and I got a bit of feedback about my correct answer. To move on, I click Continue. And these instructions say, prompt the user to enter their age, place your cursor into line 4, type your answer, and select Enter to check your work. This one is a little trickier. Let me try type your age. Got it. This feedback for my wrong answer points me in the right direction. Let's try that again. I'm going to erase what I had here and then enter your age. Perfect. I'll click continue. Let's try one more. Convert the input to an integer using int.parse and store it in the age variable. Place your cursor into line 6, type your answer, and select enter to check your work. I'm not totally sure here, so I'm going to click on hint and get some help. And the hint says use console.readline, and then an open and close parentheses, display a message asking their user for their age. Great, that helps. I'm going to click continue and type in console.readline, and I've got it. That's how you work through a guided lab. Some questions will require more complex code to complete, so make sure you're using the hint function when you need it and reviewing the feedback provided for your right and wrong answers. Have fun completing these coding challenges that put your new skills to work.
In today's rapidly evolving tech landscape, artificial intelligence plays a key role in making development more efficient and intelligent. That's where Microsoft Copilot comes in. Microsoft Copilot is a powerful AI-driven tool that can assist developers in writing, optimizing, and debugging code. In this course, you'll leverage Copilot as a thought partner and a code-generating assistant, helping you solve problems, generate code snippets, and enhance your projects. The goal is to provide you with hands-on experience using a tool that real-world developers use to improve their workflow. In the last module of this course, you'll engage in videos, screencasts, guided labs, and independent projects that integrate Copilot. These labs will take you through how to use specific prompts to generate code, optimize solutions, and solve problems. You'll be shown step-by-step how to leverage Copilot's capabilities to strategically approach the final project. During the guided labs, you'll get hands-on experience working with Copilot. These labs are structured to show you how to craft effective prompts and work with Copilot's code generation features. You'll use it to assist in writing code, refining your solutions, and debugging. This practice will prepare you for the independent work you'll do in the final project. After the videos, screencasts, or guided labs, you'll move on to independent activities where you'll take control. Here you'll use Copilot to assist with various aspects of the project. You'll be making strategic decisions, but Copilot will support you by generating code, suggesting optimizations, and helping you troubleshoot. This prepares you to work more independently while still having the power of AI to assist. The final project will combine everything you've learned in the course, and you'll have Copilot as a key tool in your development toolkit. You'll use Copilot to help you generate and refine code as you combine the concepts from earlier lessons. The project is a portfolio-ready artifact showcasing your coding skills and your ability to leverage AI in modern development workflows. To succeed in the final module, actively engage with the guided labs and practice using Microsoft Copilot effectively. The videos and prompts will take you through Copilot and equip you to apply it strategically and independently. By the end of the course, you'll be fully prepared to complete the final project and demonstrate your skills using traditional coding and AI-assisted workflows. Welcome to the course. In this video, we will discuss how you can make the most of each part of the course to set yourself up for success. Whether you watch the videos, complete activities, or work through hands-on labs, each element has been designed to help you master the skills you need to become a confident and capable developer. The first step in every lesson is the videos. You'll be introduced to new concepts, definitions, and key ideas. Watch these carefully and take notes on the important points. The videos provide the foundational knowledge you'll need to build on, so don't skip them. They'll give you the context to understand everything that comes next. After each video, complete the readings. These readings reinforce the key ideas you've just learned and can serve as job aids. I recommend printing out the readings or saving them for quick reference. They'll be extremely helpful when completing activities, working on projects, or just needing a refresher. They're not just supplementary. They help you apply what you've learned to real-world tasks. Throughout the course, you'll find small but impactful activities. These quick exercises allow you to check your understanding of key ideas. Don't rush through them. Take the time to work through these activities thoughtfully. After each, compare answers with the answer key to check how well you understand the material. This is your chance to practice without pressure. At the end of each lesson, you'll encounter practice quizzes. These quizzes are a great way to ensure you fully grasp the concepts from the videos and the readings. Use these as a checkpoint to assess how well you retain the information. If you find yourself struggling, review the videos and readings again. The goal is to build confidence and solidify your understanding before moving forward. When you need to see the material in action, screencasts guide you. These videos show you exactly how to work through certain tasks step by step. If you ever feel stuck or unsure about applying a concept, watch the screencasts and follow along. This hands-on guidance is invaluable for understanding how the code works in real time and applying what you've learned. At the end of each module, there will be graded quizzes. These are an important part of your success as they allow you to demonstrate mastery of the material. These quizzes build on the practice quizzes, and they're a great way to ensure you're ready to move on to more advanced concepts. Treat these quizzes as milestones. Passing them means you're fully prepared for the next challenge. The guided labs are where you'll take the concepts from the lessons and apply them in a controlled, hands-on environment. These labs will take you step by step through tasks, including helpful feedback and hints. The more effort you put into the labs, the more you'll get out of them. It's all about learning by doing, so take your time and ensure you understand each step before moving on. After you've completed the guided labs, it's time to test your skills with independent projects or U-Try-Its. This is where you'll apply everything you've learned without step-by-step instructions. These projects are a great way to gauge how far you've come and to put your knowledge to the test. Don't worry if you feel challenged, that's part of the learning process. By completing these projects, you'll reinforce your skills and build confidence. Finally, at the end of the course, you'll complete a culminating hands-on project that you can use as a portfolio artifact. This project will showcase the skills you've gained throughout the course and give you something tangible to present to potential employers. As you progress through the program, these portfolio pieces will become stronger representations of your hands-on experience and understanding of key concepts. Success in this course comes down to using all the tools available. Watch the videos carefully, engage with the readings, complete the activities and quizzes thoughtfully, and take full advantage of the screencasts, labs, and projects. Each element of this course is designed to help you master the material step by step. By the end, you'll have a solid understanding of the concepts and real projects to prove your skills. Remember to persist, take your time, and you'll be ready for a successful career in development. Throughout this program, you have developed your front-end skills. Now it's time to bring everything together in a Capstone project. In this project, you'll build a fully functional e-commerce application. To create a professional-grade application, you'll integrate business logic, develop an interactive UI, implement security measures, and ensure state management. In the first part of your project, you'll focus on developing the back-end logic that powers your application. This stage involves creating the core functionality that enables users to browse products, add them to a cart, and process transactions. You'll use object-oriented programming to structure your logic efficiently. Next, you'll build Blazor components that display products and allow users to interact with the shopping cart. Your Blazor components will make the shopping experience seamless, ensuring that your app's front end is dynamic and user-friendly. Now that your core components are functional, it's time to enhance the user experience. Here you'll focus on making the app visually appealing, accessible and adaptable to different screen sizes. A well-built e-commerce app must also be secure. In this phase, you'll focus on user authentication and data protection. By integrating secure coding practices, you'll ensure the data remains protected throughout the shopping experience. The last step in your project is to ensure state persistence and optimize performance. Completing this phase will make your application fully functional, reliable, and ready for final submission. Your Capstone project is an opportunity to showcase everything you've learned. This is your chance to build an application that reflects your skills and creativity. We're excited to see how you bring this project to life. Good luck and enjoy the process of developing your e-commerce app.
Welcome to Common Vulnerabilities. In this module, you will explore the security risks that threaten web applications, such as SQL injection, XSS, and CSRF. Understanding these vulnerabilities is essential for building secure and scalable applications, equipping you to identify risks, assess their impact, and implement strategies to safeguard your projects. We will begin by introducing common web application vulnerabilities, laying the groundwork for understanding the threats that compromise application security. Next, we'll delve into SQL injection, uncovering how attackers exploit this vulnerability to manipulate databases and the potential consequences for web applications. Then, we'll examine cross-site scripting attacks, or XSS, exploring how malicious scripts can target users and disrupt application functionality. After that, we'll focus on cross-site request forgery, or CSRF attacks, learning how this attack leverages user authentication to execute unauthorized actions. Finally, we will analyze real-world examples of these vulnerabilities, exploring practical strategies and tools to mitigate these threats and strengthen application security. By the end of this module, you'll have the skills to recognize and address key web application vulnerabilities, ensuring your project remains secure and reliable. Let's get started with common vulnerabilities. Every day, attackers search for vulnerabilities in web applications, exploiting weak points to access data or take control. Understanding how these vulnerabilities work is the first step in building stronger, more secure systems. In this video, we'll identify SQL injection, XSS, and CSRF vulnerabilities. Let's begin by exploring SQL injection, one of the most common vulnerabilities in web applications. SQL injection occurs when an attacker manipulates a website into executing harmful SQL commands by exploiting vulnerabilities in how the application processes user input. This vulnerability arises when an application directly incorporates unvalidated or unsanitized user input into SQL queries. By doing so, attackers can bypass authentication, access or modify unauthorized data, or even compromise the database itself. This often happens because the application doesn't properly validate or sanitize the data users enter into forms, query strings, or other inputs. For example, if a login form doesn't properly validate or sanitize user input, an attacker could inject malicious SQL code to bypass authentication and gain unauthorized access to sensitive user information. This highlights the importance of input sanitization, ensuring that user-provided data is thoroughly checked and cleaned before being used in database queries. Proper validation and sanitization are key to preventing this type of attack. Next, let's explore XSS, a vulnerability that targets users directly. Cross-site scripting, or XSS attacks, occur when attackers insert malicious scripts into a web page, typically through user inputs like forms or URLs. This vulnerability arises when a website displays user-provided content without properly validating or sanitizing it. Attackers often use JavaScript in these scripts to perform harmful actions such as showing unexpected pop-ups, redirecting users to malicious websites, or stealing sensitive information like cookies or session tokens. For example, in a comment section that doesn't filter user input, an attacker could add a script that steals login cookies from anyone who views the page. Finally, let's examine CSRF, a vulnerability that tricks users into performing unintended actions. Cross-site request forgery, CSRF, is an attack that tricks a logged-in user into performing actions they didn't intend to. This vulnerability exploits active sessions, where a user is already authenticated on a website or application. Attackers often use hidden forms, malicious links, or scripts to make users unknowingly perform actions such as changing account details, transferring funds, or making unauthorized actions, all without the user realizing it. For example, a phishing email might include a malicious link that, when clicked, tricks the user into approving a funds transfer on their online banking account without realizing it. Let's bring everything together with practical examples of how these vulnerabilities might appear in an online store. Imagine an attacker exploiting SQL injection by entering malicious SQL code into the store's search bar. Because the system doesn't properly validate the input, the code executes and gives the attacker access to the store's database, exposing sensitive customer information such as email addresses and payment details. Now consider XSS. An attacker embeds a malicious script in the product reviews section. When other users view that page, their browsers unknowingly run that script, stealing their login cookies and compromising their accounts. Finally, think about how CSRF could strike. A phishing email is sent to customers containing a hidden link. When a logged-in user clicks the link, it unknowingly approves a fraudulent order using their account, leading to unauthorized purchases. These examples show how attackers can exploit weak points in a system when proper protections aren't in place. Recognizing vulnerabilities like SQL injection, XSS, and CSRF empowers you to safeguard applications against these threats. The journey to secure coding starts with understanding the risks that could compromise your system and its users. When you log into a website to shop, log in, or share personal information, you trust that it's secure. However, vulnerabilities like SQL injection, XSS, and CSRF can undermine that trust, leading to serious consequences for both business and users. Let's explore how these vulnerabilities can cause real-world problems. In this video, we will describe the real-world impact of SQL injection, XSS, and CSRF. Let's start with SQL injection, one of the most common ways attackers exploit a website's database. This vulnerability takes advantage of how websites store and retrieve data. SQL injection occurs when attackers send malicious commands to a website's database, allowing them to steal, alter, or even delete critical information. For example, an attacker could manipulate a vulnerable login form to access sensitive data like payment details or user credentials. Now, imagine a shopping website's entire customer database being exposed simply because the login form wasn't properly secured. This highlights how devastating SQL injection can be for both users and businesses. While SQL injection exploits how websites handle data, cross-site scripting, XSS, focuses on how users interact with these websites. XSS occurs when attackers inject malicious scripts into a website, which then execute it in the user's browser without their knowledge. These scripts can perform a variety of harmful actions, such as altering the website's appearance by replacing normal content with offensive messages. For business, this can severely damage their reputation and drive customers away. Even more concerning, XSS can be used to steal login information stored in the browser. For example, attackers can hijack a user's session, the mechanism that keeps you logged in as you browse. Once they gain control of your session, they can use your account as if they were you, potentially accessing sensitive data or making unauthorized changes. While XSS manipulates how the content appears to users, cross-site request forgery, or CSRF, exploits the trust users have in their authenticated sessions. CSRF tricks users into performing actions they didn't intend to, such as transferring money or updating account details by leveraging their login sessions. These actions are carried out without the user's knowledge or consent. For example, an attacker could force a user to transfer money to a fraudulent account. Imagine donating to a meaningful cause through a trusted website, only to have your donation redirected to the attacker instead. In another scenario, attackers might change account details like delivery addresses without permission. This could result in orders being sent to the wrong location, leading to frustrated customers and eroded trust in the business. Security vulnerabilities like SQL injection, XSS, and CSRF remind us how small gaps in protection can lead to big problems. Understanding these impacts is the first step towards building safer web applications. Every action on a web application, whether it's logging in or making a payment, relies on trust between the user and the system. To protect that trust and create secure applications, it's crucial to understand vulnerabilities like SQL injection, XSS, and CSRF. In this video, we'll compare the methods, impacts, and mitigation strategies for SQL injection, XSS, and CSRF. Before we explore the comparison, let's quickly recap the key characteristics of SQL injection, XSS, and CSRF to set the stage. SQL injection targets databases by exploiting vulnerabilities in queries to access, modify, or delete sensitive data. XSS injects malicious scripts into browsers, allowing attackers to steal sensitive information or alter the content of web pages. CSRF deceives users into performing unintended actions, like transferring funds or updating account settings by exploiting their active authenticated sessions. Understanding these vulnerabilities is just the first step. Next, let's explore how they impact systems, users, and data when left unaddressed. SQL injection targets back-end data, enabling attackers to access, modify, or delete sensitive information stored in the database. XSS affects the website's interface by injecting malicious scripts and undermining user trust by stealing data or altering the website's content. CSRF exploits the trust between a user and a website to trigger unauthorized actions, resulting in unintended consequences like financial transactions or account changes. While these vulnerabilities can cause significant harm, there are effective strategies to mitigate them. Let's explore how developers can safeguard systems against each type of threat. SQL injection is mitigated by using secure input handling techniques, such as parameterized queries. Parameterized queries are SQL queries where placeholders are used for user input, ensuring that any input provided is treated as data, not as executable code. This prevents malicious commands from being executed as part of the query. Another effective technique is using stored procedures, which are predefined SQL scripts stored in the database. By controlling the query structure within the database, stored procedures limit opportunities for malicious injection. Input validation also plays a key role by ensuring that user inputs conform to expected formats and rejecting or sanitizing harmful inputs before they reach the database. XSS can be mitigated by validating and sanitizing all user inputs to ensure they meet expected formats and do not include harmful code. Additionally, escaping output ensures that any data displayed on a web page is treated as plain text rather than executable scripts, preventing malicious scripts from running in the browser. Output escaping works by encoding special characters like a left bracket and a right bracket, so they are displayed as text instead of being interpreted as code. CSRF is mitigated by implementing unique, randomly generated tokens in forms or requests. These tokens verify that actions are intentionally authorized by the user and cannot be triggered by attackers. Since the token is tied to the user's session and validated on the server, any request without a valid token is rejected. By comparing these vulnerabilities, we've uncovered how they target different parts of a system and require unique defenses. This foundational knowledge prepares you to secure web applications effectively and safeguard user trust. Each time an application processes user input, there's a risk it could be manipulated by attackers to exploit vulnerabilities. SQL injection is one of the most dangerous techniques, turning simple inputs into tools for breaching databases. In this video, we'll explain how SQL injection exploits occur through specific query manipulations and vulnerable code. To understand how SQL injection works, let's examine how applications create queries using user inputs. Applications often generate SQL queries dynamically by incorporating user inputs directly into the query. For instance, when you log into a website, the system might run a query. In this query, input 1 and input 2 are replaced by the username and password you provide. However, if these inputs aren't properly validated or sanitized, an attacker can manipulate them to make the query behave in unintended, potentially harmful ways. SQL injection attacks often start by bypassing authentication, but they can quickly escalate to extracting sensitive information or even destroying data. Let's break down how these techniques work in practice. Attackers manipulate user inputs to alter the behavior of SQL queries. For instance, in a login form, an attacker might enter an input like this, which changes a query like this. Select asterisk from users where username equals input 1 and password equals input 2. Here, the username and password values are valid, expected inputs like input 1 and input 2. As you can see, this is where things go wrong. Select asterisk from users where username equals input 1 or 1 equals 1 dash dash. Notice how the value of input 1 was changed to be input 1 or 1 equals 1 dash dash. This includes a quote and the condition or 1 equals 1, which is always true. The double dash is SQL syntax for a comment, effectively ending the query and turning the rest into a comment. The condition 1 equals 1 is always true, causing the database to bypass password verification and grant access. Beyond bypassing logins, attackers can exploit this technique to manipulate queries and retrieve sensitive data. SQL injection doesn't just expose sensitive data, it can also delete it, allowing attackers to cause significant disruption and data loss. For example, an attacker might inject semicolon drop tables users semicolon dash dash. This command starts with a quote and a semicolon, which ends the main query and then starts another query using the drop command. Then it ends the drop command with a semicolon, then 2 dashes so that any other SQL will be seen as a comment. When injected, the query becomes select asterisk from users where username equals blank, drop tables user semicolon dash dash. When injected, the query terminates the original one and introduces a malicious command, leveraging SQL syntax to perform unintended operations. The drop table users command deletes the entire users table, wiping out all user data. The result? Significant disruption to the system's functionality and a major breach of trust. Beyond bypassing logins, attackers can modify queries to retrieve sensitive data. For instance, injecting single quote, semicolon, select credit card numbers from payments dash dash. This injection starts with a quote and a semicolon to terminate the current query, followed by a new query that attempts to retrieve sensitive information, such as credit card numbers. While this demonstrates how SQL injection works, it's important to note that real-world databases often have safeguards, like encryption for sensitive fields or permission restrictions, to prevent such exploits from succeeding. It tricks the database into executing an unintended query. Instead of processing the original request, it retrieves sensitive information, such as credit card numbers, from the payments table. Understanding how SQL injection works reveals the cracks in insecure systems and emphasizes the importance of proper safeguarding. By identifying these vulnerabilities, you can take the first step toward building secure, resilient applications. Every day, web applications are exposed to hidden threats that can compromise sensitive data and disrupt critical services. By adopting secure coding practices, you can design systems that are better equipped to defend against attacks like SQL injection. In this video, we'll describe secure coding practices that mitigate SQL injection. Securing your application begins with controlling the data users provide. When attackers can inject harmful inputs, they exploit vulnerabilities to compromise your system. This is where input validation plays a crucial role. Input validation ensures that user inputs conform to expected types and formats before they're processed. By blocking harmful data at the source, input validation guarantees that only safe and valid inputs reach your system. For instance, think of a registration form that only accepts emails with the @ symbol and valid domain names. This ensures your application only processes clean, expected data. Input validation ensures data is clean, but it doesn't guarantee that data is handled safely in database commands. And that's where parameterized queries come in. Parameterized queries are a technique that keeps SQL commands separate from user inputs, preventing attackers from manipulating queries. This approach ensures that user inputs are always treated as data and never as executable commands. Imagine a shopping app where users search for items. By using parameterized queries, the database treats user inputs as data, ensuring they are handled safely and preventing unauthorized access to sensitive information. Once your queries are secure, ORMs, or object relational mapping tools, can further streamline and safeguard database interactions by automating query generation. Object relational mapping, or ORM tools, are frameworks that simplify database interactions by letting developers use code instead of raw SQL. ORMs handle complex queries behind the scenes and securely manage data access to prevent vulnerabilities like SQL injection. For example, a blogging platform can use an ORM to manage posts securely without needing to write SQL commands for each action. While some developers prefer interacting directly with SQL commands for finer control, ORMs provide a structured and automated way to handle common database operations. When used correctly, ORMs help reduce the risk of SQL injection by parameterizing queries and abstracting raw SQL interactions. It's also important to note that ORM tools are just one part of a secure database strategy. Even with an ORM in place, the database user account that the application uses should have limited permissions, restricted to essential actions like reading and writing data. This ensures that even if a SQL injection attack bypasses all other mitigations, the database server would still block destructive commands, such as dropping tables or altering schemas, providing an additional layer of security. The backbone of secure applications lies in thoughtful design and proactive measures. Techniques like input validation, parameterized queries, and ORM tools safeguard your system, ensuring trust and reliability in the face of evolving threats.
Each time an application processes user input, there's a risk it could be manipulated by attackers to exploit certain vulnerabilities in your programs. SQL injection is one of the most dangerous techniques. It turns simple inputs into tools for breaching and then exploiting databases. In this screencast, I'm going to look at a SQL injection and how it works. And I'll show you examples of a vulnerable endpoint and then a secure endpoint. So I have a very simple Node.js application here. I'm going to run this on a Node server. And this application creates a couple of endpoints that we can use Postman to send data to. It queries a MySQL database that's running on this machine as well. I have a table called users, and there's some dummy data in that table. And I can use these endpoints to get data from the server and then send it back to the calling application. So I've got two endpoints in this application. One's called the login vulnerable to illustrate the SQL injection attack. And then the other one is a secure endpoint, which illustrates how to do this properly so that you don't have the problem with the injection attack. The way the injection attack works is that the username and password is passed to the endpoint in the body of the request. You're just writing out to the console what the username and password are. And then the query is constructed in this endpoint code using the username and password that we pass in. So you can see we have a query called select all from the users table where the username and password are certain things to gain access. If the username and password aren't right, then you'll get an invalid response. If they're the correct username and password, then you'll get access. Now the problem with this is that we're constructing the query out of the parameters that we pass in. So we can actually exploit this by modifying the select statement using SQL code. We can use SQL commands in the body that we're passing in to change the select statement so that we can gain access without using the right credentials. The username is root and the password's name is your password. That's how I gain access to the database. Obviously, these are not really great username and passwords. We would want to change these in a live environment, but for demonstration purposes, this is what should get us access to the database. Okay, I'm going to start my Node server so that we can hit our endpoint using Postman, and then we'll send credentials over to the vulnerable endpoint and see if we can log in without actually using the right credentials. I'm going to start my server. So this is going to be running on port 3000, and I'll go over to Postman. There's the endpoint, login vulnerable. I'm going to send a post request. Now, here's what I'm doing in the body. I'm going to send a blank, but notice I'm sending or 1 equals 1 and then dash. What this is going to do is modify that SQL statement here. This is going to say select star, select all from users where username equals blank or 1 equals 1, and then the dash is going to comment out the rest of the phrase, and password equals password. So it's going to completely ignore that. Okay, so what we're going to end up getting is select star from users where username equals blank or 1 equals 1, which means true. We're injecting an OR statement where the OR statement always evaluates as true, and that's going to allow us to access the server without sending valid credentials. So now when I press the send request, notice that it said login successful because it evaluated that OR statement as true and allowed us to access the server. Const rows awaits DB query, so does it query the database? It attempts to do so with that select statement. If the row's length is greater than 0, meaning that it returns some rows, then the login is successful. If it doesn't, then it gives us invalid credentials. But notice we got the message login successful, meaning it was able to query the database. The injection attack is actually sending SQL statements to this endpoint, modifying the select statement, and gaining access to the database. Now, under the secure option, we are still sending in the username and password, but we're not modifying the query itself. We're actually using this construct here where we have the query as a separate item, and then username and password are sent as statements that get injected into the query after the fact. So it's not using the username and password as a part of the query. It's using the username and password as an option for logging into the database. So it's not actually modifying that select statement. So if someone sends invalid SQL or tries to send SQL that can modify the select statement, it actually won't change that select statement. So we can test that by going back into Postman. I'm going to change to the secure endpoint. And if we send these invalid credentials to that secure endpoint, it should fail. So it does tell us we have invalid credentials because we're not sending over the proper credentials for a user in the database. So I'm going to send over now a particular user. I'm going to use admin. And instead of sending this SQL code, we're going to use a username that we know exists in the database. And I think the password is password123. So now, because we're sending the username and password for a valid user in the database, it should let us know that the login was successful. And there we have it. So because it's now a valid user, we can access the database. In here, this is constructed as we pass that body over. And when the row's length is greater than 1, it has returned a user. Then we get our message there. We've got some console logs here to help us out. So that's how a SQL injection works, and it really comes down to how the code is constructed. We certainly don't want to pass in the username and password and use that to construct our SQL statement. We want to send these username and passwords over as parameters and then use them in the statement that way. And that will help prevent SQL injection attacks.
Every time you interact with an application, whether it's filling out a form, leaving a comment, or making a purchase, you trust that your input will be handled securely. But what happens when that trust is broken and a malicious script exploits vulnerabilities and how the inputs are processed? In this video, we'll explain the mechanisms of XSS attacks and how they exploit vulnerabilities in user input. To understand this, let's define cross-site scripting, or XSS, and explore why it's one of the most common web vulnerabilities. Cross-site scripting is a vulnerability where attackers inject malicious scripts into trusted websites, which are then executed in the browsers of unexpected users. This allows attackers to manipulate content or steal sensitive data. Now that we've introduced cross-site scripting, let's explore how attackers exploit it, starting with script injection. This technique involves embedding malicious JavaScript into input fields that don't properly validate or sanitize user-provided data. Imagine a comment box on a website where someone enters a script tag with alert XSS. If the website doesn't validate or sanitize this input, the script becomes part of the page's code. In this example, the malicious script tag is embedded into the div element, which represents a comment on the web page. Instead of displaying the comment as plain text, the browser interprets the script tag as executable code. So when another user views the page, the browser executes the malicious script tag instead of treating it as plain text, triggering the attack to exploit this vulnerability. But the damage doesn't stop there. XSS attacks can also target sensitive data stored in your browser, such as cookies. Cookies are small pieces of data stored by your browser to keep you logged into a website or remember your preferences. Attackers can exploit XSS to steal these cookies, allowing them to impersonate the user. For example, consider that after you log in, your browser uses cookies to identify you during your session. If a malicious script steals this data, an attacker can use it to impersonate you, gaining access to your account without needing your password. An XSS attack doesn't just steal data, it can also alter the way the web page functions. For instance, imagine browsing a website and noticing that the login form appears slightly different. The attacker script may have replaced the legitimate form with a fake one designed to steal your credentials. Now let's explore how these steps, script injection, execution, and hijacking, work together in a real-world scenario. Imagine an online comment section where attackers inject script tags into their comments. When users view the page, the malicious script executes in the browser. This could result in the script stealing session cookies or displaying a fake login form to collect credentials. To address the issue, the platform implements input validation, prevents scripts from executing in the browser. By understanding how cross-site scripting attacks exploit user input and execute malicious scripts, you've taken the first step towards recognizing and addressing one of the most pervasive web application vulnerabilities. Building secure systems starts with knowing how they can be attacked. Every time users interact with your web application, they trust it to be safe. But cross-site scripting or XSS attacks can break that trust, exposing users to harm and damaging your application's reputation. In this video, we'll describe how to prevent XSS attacks using input validation, encoding, and CSP. Preventing XSS attacks starts with controlling the data users can enter into your application. The first line of defense is input validation, which ensures input fields only accept valid and expected data. This process blocks harmful input before it can affect your system. To implement input validation, set clear rules for what data is acceptable. Validate inputs both on the user's device in the browser and on the server, and either reject or clean up anything unexpected. For example, if a website requires a username, it can validate the input to ensure it only contains acceptable characters, such as letters, numbers, and optionally specific symbols. Any unexpected input, like unauthorized scripts, should be rejected or sanitized. While input validation helps block harmful data, some inputs might still pass through or be stored for later use. To ensure stored data is safe to display, we use HTML encoding. HTML encoding converts potentially harmful characters into safe versions that browsers treat as plain text. This ensures that even if malicious input is stored, it cannot harm your application. For example, if someone tries to enter a script into a comment box, encoding changes the characters into symbols that display as harmless text instead of running as instructions. Encoding ensures displaying content is safe, but attackers might still try to execute unauthorized scripts. To block these, we use a broader solution, Content Security Policies, or CSP. Content security policies are a secure measure that limits what content can run on your web page. It prevents attackers from running unauthorized or harmful scripts by enforcing strict rules about what is allowed to load. For instance, you can configure your application to only allow scripts and resources from trusted sources, such as your own website. Set up a CSP using tools that allow you to define trusted sources for your content, such as specific websites or servers. Define trusted sources for your content, such as your website, or approve third-party services. Test your settings in report-only mode to safely check how your CSP will work. In this mode, the CSP doesn't block anything on your site, but instead logs any issues or violations it detects. This lets you review what might need fixing or adjusting before you fully enforce the policy, ensuring a smoother implementation without breaking your website. For example, An online store might use CSP to allow only trusted payment gateways and internal scripts to operate, ensuring security without disrupting functionality. Securing your web application starts with validating all inputs, encoding user-generated content, and using CSPs to block unauthorized scripts. Regularly testing for vulnerabilities ensures these measures work together to provide a strong defense against cross-site scripting attacks. By implementing these strategies, you create a safe environment where your users and their data are protected.
When you're designing a website, you expose yourself to a lot of different people, including everyone on the internet if your app is live. And that could include threat actors that are out to do harm. It's important to make sure that your web applications are as secure as you can make them. There's a lot of good devices and tools that you can use today to ensure that your website remains safe. In this screencast, I'm going to show how a cross-site scripting attack can occur. And that's generally where a threat actor tries to insert code into your application to do things that are destructive, to either steal or delete data or any number of things. So I'm going to show you how that works in this simple application and some techniques we can use to mitigate that or to solve for that. I have a very simple app here. I have an index.html page, which has a form and with a label, a text area, and a button. This is designed as a comment form so that users can add comments. And then it uses this app.js file to do the submission. So we're attaching an event listener to the button. When the user presses the button, it runs this function. We're going to look at this first function up here, add comment. It will take the element comment, the value of that element, and it will insert into a div, inner HTML, for the comment section that's on our HTML page. So here's the comments div and then the link to our source. So what this is going to do is just add another div with whatever we input into the box. So let's take a look at how this works. So I'm going to use this show preview extension that I've installed to display our web page. There's our comment box, and I can add a comment and it will show up on the page. So easy and simple. And when we do a simple comment like that, it works well. Now let's suppose we wanted to insert HTML. We were thinking about this from a threat assessment perspective, and the way that the JS is written is it takes whatever we put in the comment box and it will output it between two div tags on our page. Now if we do something innocuous like just add a comment, it shows up nicely on the page. But we can also think about scenarios where we add something like HTML tags that can do some work. So let's just take this simple one, an image. And I've got an image.jpg in my site. We'll go back to the page, and instead of putting just text in, we'll put in some HTML. Now because the image exists, when I submit that, it shows the image on the page. So what it did was it went to that function, add comment. It took the HTML that I had in the comment box, and it put it between these two div tags, and we saw the image on the page. So it's actually taking that HTML and rendering it for us. Now this image is innocuous in some ways. It's not really what we want it to do, because adding HTML to a comment box like that and rendering it to our page generally isn't how a comment box should work. But the way we've designed the page, that's exactly what happens. Now thankfully this works because we had the image and it's fairly innocuous. It doesn't do anything. But we can also imagine a scenario where a threat actor uses something a little bit more intense. So let's just take this one now. Let's take a look at this new tag. So this is also an image element, but instead of putting a valid image in the source, the code uses the letter X. So what happens is when the browser tries to render the image X, there is no image X. So it's going to fail and it produces an error. And the error is actually more code. In this case, we're just doing a simple alert, but you can imagine that the on error does something nefarious. It steals data, it erases data. It does something on the server that we don't want it to do. But you'll see how this code will run when we put it in here and use it because it's running in the browser with the source of X. It's going to fail and then that's going to cause problems for our application because it's actually going to run more HTML code. So let me go to the browser and we'll add that new element into our comment box. And when we submit, it actually produces an alert box and it has the text in there. Again, an alert box, it's not a threat. It's very innocuous, but you can imagine code where it could be very dangerous if someone were willing and able to insert code that we didn't want in that application, including JavaScript that can do some work. So there's a way that we can solve for this, and that's in this other secure function called add comment secure. And you'll notice that there's a constant called sanitized input. So what we're doing here is we're taking whatever inputs in the box, the comment input, and we're going to replace certain tags so that anything that appears to be an HTML tag will get repurposed. It's going to use this vocabulary to replace the actual brackets with something that the browser can actually render, but that can't be run as code. In our inner HTML, we're actually rendering the sanitized input to replace the actual brackets with a new value that the browser knows how to handle, but it's not going to run it as code. So in order to fix this, we'll have to do add comment secure in our handler. Then we'll go back to the page, refresh, and then we'll paste our code back in here. So this is the same code that has the image with the source of X, and I'll click submit. And you'll notice now that it rendered it as HTML because we sanitized it first. It didn't actually produce that alert box because the browser didn't see it as code. It saw it as HTML string, but it rendered it as a regular string to the browser, just if we put any other comment in here. So that's a way that we could prevent an attack by just sanitizing the input before it gets rendered to the browser, even if we're using this type of a construct. I'm going to go back to our original add comment function. And I'm going to add another line here. This is a CSP or Content Security Policy meta tag. And I'm going to comment this out. By the way, I used Control / on a Mac, it's Command /. You can comment or uncomment using that simple keystroke. It just makes it easier. You can also select multiple lines. So this CSP is going to prevent anything that looks like code from being rendered when it's submitted through an input box. So it's actually looking for these types of problems for us, so we don't have to sanitize. It's always best to sanitize as well as use a CSP, but the CSP is a way that browser manufacturers and people that worry about how the HTML language is developed can help us to ensure that the input that's being submitted is not threatening. So I'm going to go back to the page now. And I'm going to put that code back in, the one with the image with a source of X. Also, we're using our add comments. This is the one that produced the alert before. We're using the same one, but we've added that CSP now. Let's see what happens. Notice that it tries to render the image X. It's not there, so it shows this little icon. But also notice that the alert did not occur. And that's because the CSP protected the site. So if we go into Developer Tools, we can actually see a message from the browser: refuse to execute inline event handler because it violates the following content security policy. So there's the CSP, and an unsafe inline keyword is what we need to use to get that to work, but we don't want it to work, so we're not going to put that in our CSP. But it did detect that there was a problem with the input, and so it refused to execute the handler because of that. So that's where the CSP can actually help protect the site as well by being aware of the input that's being submitted. Building a website, you should put security at the top of your list and make sure that all of your input is sanitized and that you're using things like a content security policy to make sure that your site and your data is safe.
Every time you log into a website, you trust it to protect your information and ensure your actions are secure. But what happens when attackers exploit that trust, using your active session to perform unauthorized actions without your knowledge? In this video, we'll explain the mechanics of CSRF attacks and why active user sessions are vulnerable. To understand how these attacks happen, let's first recap what CSRF is and how it leverages a user's trust in a website. CSRF, cross-site request forgery, is a web security attack that tricks users into performing unintended actions on a website where they're already logged in. This attack exploits the trust a website places in the user's browser by taking advantage of their active session. The consequences of a CSRF attack can be serious, ranging from transferring money to changing account settings, all without the user's consent. Now that we've remembered CSRF, let's explore how these attacks occur, starting with session exploitation. Attackers take advantage of active user sessions by crafting malicious requests that rely on the victim's authentication tokens, such as cookies, to perform unauthorized actions. For example, imagine you log into your online bank. An attacker sends you a link to what appears to be a harmless website. When you click the link, it triggers a hidden request that uses your session token to approve a money transfer to the attacker's account. The server processes the request because your session token is automatically included, trusting that the action is legitimate, even though you never intended to authorize it. Once attackers exploit an active session, their next step is to craft requests that appear legitimate to the server. To deceive the server, attackers design requests that mimic real actions taken by the user. For instance, an attacker might embed a hidden form on their website. If you visit that page, your browser could unknowingly submit the form, transferring money or changing your password because the request is tied to your active session. The server processes it as if it were a legitimate action intended by you. Attackers might use a hidden form to submit data without the user's knowledge, silently sending a transfer request to a bank server. The form tag specifies the target server. For example, action equals https://bank.com/transfer. And the method, for example, method equals post to send the request. Hidden fields such as input type equals hidden, name equals amount, value equals 1000, pre-fill details like the transfer amount and the attacker's account. When the victim visits the malicious webpage or clicks a disguised link, JavaScript submits the form automatically. The victim's browser includes their session token, such as a cookie, making the request appear legitimate to the server. The transfer is processed as if the victim authorized it, without them ever visiting or interacting with the form. Another method attackers use is embedding malicious links in emails or websites. A phishing email of this kind is carefully designed to resemble legitimate communications from trusted entities, such as a bank, often claiming to provide urgent account updates or critical information. The malicious link, often disguised as a routine action like view your statement, is embedded within the phishing email. It uses an anchor tag with an href attribute that specifies the target URL, such as https://bank.com/transfer, and includes query parameters like amount equals 1000 and to account equals attacker_account to pre-fill the details of the unauthorized request. When the victim clicks the link, the browser automatically sends a request to the specified server, including session cookies from their active login. Because the session token is valid, the server processes the request as if it were legitimate. This allows the attacker to exploit the victim's session and carry out unauthorized actions without their knowledge. The success of a CSRF attack depends on specific conditions being met. Let's explore these conditions to understand how they enable the attack to succeed. First, you need to be logged into the target website. Imagine being signed into your social media account. An attacker could exploit your active session to post harmful content as if it were you. Second, the website server must lack proper protections, like CORS. Without mechanisms to verify the source of a request, the server blindly accepts the forged request as if it were legitimate. Finally, the attacker needs to interact in some way, such as clicking a link or visiting a web page that secretly submits the forged request. When these elements align, an active session, an unprotected server, and user interaction, the attack is successful. Now that we've examined how these attacks are carried out, let's understand why active user sessions are particularly vulnerable to CSRF. CSRF attacks work because browsers automatically send authentication tokens like cookies with every request to a website. Think of these tokens as a digital badge that provide your identity to the server. When a malicious request is sent, the token is included automatically, making it seem legitimate. For example, if you're logged into an email account, a forged request could delete emails or send unauthorized messages, all because the server trusted the token sent by your browser. To understand how dangerous these attacks can be, let's explore a real-world example. A banking platform without CSRF protections on its money transfer feature was exploited by attackers. They sent phishing emails to users disguised as official bank communications and tricked them into clicking malicious links. Each click triggered a hidden form that transferred funds from the user's account to the attacker. Because the banking platform didn't verify the origin of these requests, it processed them as legitimate transactions. This example highlights how easily CSRF can lead to significant financial losses and reputational damage if proper safeguards aren't implemented. Understanding the mechanics of CSRF attacks demonstrate how easily an attacker can exploit an active session to perform unauthorized actions. With this knowledge, you're now better equipped to identify vulnerabilities and take the necessary steps to protect your applications and users from these subtle yet dangerous threats. Every interaction on a web application relies on trust. But what happens when that trust is exploited? Cross-site request forgery, or CSRF attacks, manipulate this trust, forcing users to perform harmful actions without their consent. Understanding how to prevent these attacks is critical to building secure applications. In this video, we'll describe techniques to prevent CSRF attacks, such as CSRF tokens and same-site cookies. Preventing CSRF attacks begins with verifying that every user request is legitimate. One of the most effective ways to do this is by implementing CSRF tokens. CSRF tokens are unique values embedded in forms to verify that only authorized actions are processed. These tokens act as a secret key shared between the server and the user. To use CSRF tokens, include a hidden token in every form sent to users. When one of these forms is submitted, the server validates the CSRF token to confirm it matches the one that is issued. If the token is valid, the request is processed. Otherwise, it's rejected, blocking unauthorized submissions. To further protect user sessions, you can control how cookies are sent. Same-site cookies restrict cookies from being sent with cross-site requests, blocking unauthorized access. By setting the same-site attribute to lax or strict for session cookies, you can limit their exposure to cross-site attacks. This ensures cookies are only sent when interacting directly with your application. For example, setting session cookies with same-site equals lax ensures they are only sent during direct interactions with the application, such as when a user clicks a link to navigate to the website. This means that the cookies won't be included with other requests made from other websites, such as those triggered by hidden form or malicious script. By restricting when cookies are sent, same-site equals lax reduces the risk of attackers exploiting cross-site requests to hijack user sessions. While same-site equals lax provides a good balance between security and usability, same-site equals strict offers even stronger protection by ensuring cookies are never sent with any cross-site request, including link navigation. In addition to controlling how cookies are sent, verifying that requests originated from trusted sources adds another layer of security. One way to achieve this is by using referrer headers, which provide information about the web page or source that initiated the request. For example, when a user submits a form or clicks a link, the referrer header in the request indicates the URL of the page where the action started. The application can examine this header to ensure that the request originates from an authorized domain. If the referrer header doesn't match the expected domain, for instance, if the request comes from an untrusted website, the application can block it to prevent unauthorized access to sensitive data. This technique is particularly useful for identifying and stopping CSRF attacks, where requests are often forged from external sources. However, it's important to note that referrer headers can sometimes be stripped or modified by browsers or network configurations, so this method is most effective when combined with other security messages like CSRF tokens. For actions requiring extra security, user confirmation provides an additional layer of protection. This ensures that critical actions, such as updating sensitive information or transferring funds, are performed by only the account user. For instance, when a user attempts to update their passwords or change account details, the application might require them to re-authenticate by entering their credentials again or completing a verification step, such as a one-time code sent to their phone or email. This prevents attacks from exploiting an open session to perform unauthorized actions, even if they have access to the user's browser session. Protecting users from CSRF attacks means safeguarding their trust and their actions online. By combining techniques like CSRF tokens, same-site cookies, referrer validation, and user confirmation, you can create a layered defense that ensures security and reliability in your applications.
Creating a safe website takes a lot of intentional work to make sure that your site is designed to protect from threat actors that might try to steal data, erase data, or worse. In this screencast, we're going to look at a cross-site request forgery attack. And this tricks a user's browser into making unintended requests, and many times without the user's knowledge. I have a very simple site set up here, a node server. I'm using server.js as the code behind. And then we have a simple page here. This page will trick the user by having a submit button that says click here for a free gift. And when the user clicks the button, it actually does work behind the scenes from server.js. And this just obviously is fake, but it could transfer money or data or whatever from the server to the target without the user's knowledge. You can imagine a threat actor having inserted this page on a site that otherwise looks very normal, and the user is browsing around on a site they trust, and then they get to this page that the hacker has inserted, and the hacker has made sure that the page looks like the rest of the site, and when the user clicks on the button, something bad happens. So let's take a look at how this would work. So the user sees the button, click here for a free gift. They think it's a part of the site that they're browsing. They click on the site, and then in this fake example, $1,000 is transferred to attacker 123. Now what's happened here is that this page and the code behind it looks normal, looks like it's something that the user might see on a site, but in fact, it's been a page and some code that the attacker has inserted. Now, one way we can prevent these types of attacks is to use a token in every request. A token is something that validates that the page that the user is interacting with is actually from the site. And you can create these tokens and then make sure it's always transferred with the body of the request. So I'm going to uncomment out this code. And this is the code that we'll use to perform a safe interaction and to make sure that any request does have this token included with it. You'll notice that the token's created, and then we're going to use that token in our application. There's a secret key here, which can be secured behind a database or other ways of securing that key. But the page has to use this token that's created with this secret key in order to make any requests or send any responses to any other site. So that's what this token is doing for us. Then we also have a form here that will only interact with an endpoint. You'll notice that we have two endpoints now, two post endpoints that use the transfer and the transfer route. The page will just use the post that's first in line, whatever one encounters first. And for this one, we're just going to demonstrate that it's a CSRF protected route, but either route would work in this case. So let's go back to our page. I'm going to start with demo.html. Now, this page does not have the token included in the request. So when we click the button, we're going to get an error back that says that the CSRF token is invalid. So the server now expects that token for any response and any request that's made. And because the page doesn't include the token, and it can't because it doesn't have the secret word to create the token, so the page isn't going to allow it to work. This code also includes a valid form, and you can see that this is in the code itself. We've developed this form that uses the token. You can see there's a value equals parameter, and we have the request.csrf token included in that form. So when the form is submitted, that token is going to be sent with it. So we can go to that form now. I'll route to the form. And this is a friendly form. This one is one that belongs to the site, and we'll request a token. So we can send it to a friend. And when I hit transfer, this will allow it to work because we have included the token in the requests. So by using this CSRF token, we can protect the site by ensuring that the requests and responses are being sent by the site that they were intended to be sent from. And that's another way that we can protect the site from malicious intent. We're doing one more thing here. We're also including a parameter where we specify that the cookies that are used in responses and requests only must come from the same site from which the requests and responses originate. By adding that parameter, then a malicious actor can't inject a cookie and then use that cookie for unauthorized intent. So that is another way that we can protect the site by adding that parameter to our session. So these are just a few ways that you can protect your website from cross-site request forgery and keep your site and your data more secure.
A single vulnerability can unravel years of trust, exposing sensitive information and leaving companies scrambling to recover. SQL injection attacks are among the most devastating threats, exploiting unnoticed flaws to access and compromise critical data. In this video, we'll analyze a SQL injection attack. One of the most significant examples of a SQL injection attack occurred in 2008 when Heartland Payment Systems, a major credit card payment processor, was breached. Attackers exploited vulnerabilities in the company's systems, injecting malicious SQL code to bypass authentication and access sensitive databases. This allowed them to install malware and steal data for over 100 million credit cards and debit card accounts, making it one of the largest data breaches in history. How exactly did the attackers exploit this vulnerability? Well, let's break it down. At the time, many organizations, including Heartland, underestimated the importance of securing web applications, often over-relying on firewalls while leaving input validation and database queries vulnerable. Attackers exploited these vulnerabilities, likely injecting malicious SQL code through input fields that were not properly validated or sanitized, allowing them to bypass authentication and gain access to sensitive databases. This gave them a way to manipulate database queries. Instead of verifying credentials, the database executed the injected SQL code, granting unauthorized access to sensitive systems. Once inside, the attackers moved laterally within the network, taking advantage of insufficient segmentation between systems. They used similar techniques to execute additional queries and retrieve sensitive information, ultimately stealing data from millions of credit and debit card accounts. The consequences of this breach were catastrophic, not just for Heartland Payment Systems, but also for its customers. Here's what happened. Over 100 million credit and debit card accounts were compromised, exposing cardholder names, card numbers, and expiration dates. Customers lost trust in the company, and Heartland faced significant reputational damage. The breach resulted in massive financial penalties, with Heartland paying over $145 million in fines, legal settlements, and recovery costs. Recovery efforts spanned months and included rebuilding their database infrastructure, implementing stricter security measures, and addressing customer concerns. The breach serves as a reminder of how a single SQL injection vulnerability can lead to widespread and devastating consequences. While the impact was severe, the good news is that SQL injection attacks are entirely preventable. Let's explore some effective strategies to stop them. Input validation ensures that users can only provide data in the expected format, reducing the risk of malicious input. SQL injection attacks don't just happen through visible form fields. They can also occur via hidden parameters like URL query strings. For example, imagine a web application that uses a query string to identify a specific item, such as a shopping cart. If an attacker modifies this query string to include unexpected content, like a command to retrieve all items instead of one, the system might execute the malicious request if the input isn't properly validated. By validating input to ensure query string parameters like item identifiers only match the expected format, for example, a number, attackers are unable to exploit these hidden entry points. This demonstrates why validating all inputs, including query strings, is a crucial first step in protecting applications from SQL injection vulnerabilities. Parameterized queries are the first line of defense against SQL injection. They ensure that user input is treated as data completely separate from database commands. This approach eliminates the risk of SQL injection by neutralizing attempts to manipulate SQL syntax. Modern frameworks like ADO.NET and Entity Framework in .NET provide built-in support for parameterized queries, making this technique straightforward to implement. Escaping special characters like single quote, double quote, semicolon, and a double dash and pound sign converts them into harmless text, preventing them from being interpreted as SQL commands. However, escaping is considered a supplemental measure and should not be relied on as the primary defense. Modern techniques like parameterized queries are far more effective and robust. Frameworks like Entity Framework in the .NET platform simplify database interactions by securely generating queries and handling parameterization automatically, reducing the risk of SQL injection. Similarly, database stored procedures can minimize the risk of SQL injection by encapsulating query logic and separating it from user input. However, developers must avoid manually concatenating SQL strings within stored procedures, as this can just reintroduce vulnerabilities. When combined, these strategies form a robust defense against malicious input. If the company from our earlier example had implemented these measures, the SQL injection vulnerability could have been prevented, significantly reducing the risk of such an attack. SQL injection isn't just a technical flaw, it's a gateway for attackers to dismantle trust and disrupt systems. By implementing secure coding practices, organizations can not only prevent these attacks, but also protect the data and trust that are at the core of their success. Cross-site scripting attacks can turn trusted websites into dangerous traps, exploiting even the smallest vulnerability to compromise user data and trust. Understanding how these attacks unfold is the first step towards building secure web applications. In this video, we'll analyze a cross-site scripting injection attack. Let's examine how a cross-site scripting attack unfolded on a major social media platform. In 2005, a user created what became known as the MySpace worm, exploiting a vulnerability in MySpace's input handling. The attacker embedded malicious JavaScript into their profile's About Me section. When other users viewed the infected profile, their browsers executed the malicious code, causing it to replicate across their own profiles. In this case, the attack didn't just spread rapidly, it added this user as a friend to infected profiles and displayed the message, "Sammy is my hero," defacing over 1 million profiles in less than a day. This attack became a landmark example of how cross-site scripting vulnerabilities can compromise a platform's functionality and trust on an unprecedented scale. The attack succeeded due to critical weaknesses in MySpace's approach to handling user input and rendering output. These flaws created opportunities for malicious code to be embedded and executed, bypassing security controls. Let's break down the key vulnerabilities that made this attack possible. MySpace allowed users to customize their profiles by entering text into fields like the About Me section. However, the platform failed to validate or sanitize this input. This oversight allowed the attackers to embed malicious JavaScript directly into their profile. For example, the attacker inserted harmful code into the About Me field, which the platform stored in its database exactly as entered. Since the input wasn't filtered or sanitized, the malicious script executed in the browsers of other users who viewed the attacker's profile, triggering the worm's rapid spread. When the profile information was displayed on a user's page, MySpace failed to encode the malicious input properly. Instead of treating the attacker's JavaScript as harmless text, the browser processed it as executable code. This allowed the script to execute every time someone visited an infected profile, demonstrating the potential of cross-site scripting attacks to exploit vulnerabilities, whether by replacing malicious code, manipulating user profiles, or even stealing session cookies in other cases. Without a content security policy, a concept not yet widely implemented in 2005, MySpace lacked the ability to restrict which scripts could execute within the platform. This allowed the malicious JavaScript to run with the same permissions as legitimate code. As a result, the attacker's script was able to spread unchecked manipulated profiles and compromise user sessions, significantly amplifying the damage. While these vulnerabilities created opportunities for the attacker, effective mitigation strategies can prevent such incidents in the future. Protecting against cross-site scripting requires implementing several key techniques to strengthen your application security. Input validation ensures that users can only enter safe data, such as letters, numbers, or specific characters allowed by the application. For example, restricting inputs in fields like profile descriptions or comments can prevent harmful scripts from being introduced. Encoding ensures potentially dangerous characters, such as left angle bracket, right angle bracket, and single quote, are converted into their harmless text equivalents, like &LT, &GT, and &#39, preventing them from being executed as code. This ensures that even if malicious input makes it into the system, it will not execute as code in the browser. Together, these techniques create a strong first line of defense against cross-site scripting attacks. A content security policy acts as a rulebook for browsers, specifying which scripts are allowed to execute. For instance, a CSP might permit scripts only from your own domain and block any from untrusted resources. In the case of MySpace, implementing a CSP could have restricted the execution of the attacker's script and stopped it from spreading. At the time of this attack in 2005, CSPs were not yet widely implemented, but today they are a crucial tool in defending against cross-site scripting. By limiting what scripts browsers can trust, CSPs dramatically reduce the impacts of cross-site scripting vulnerabilities. Regular security audits ensure that vulnerabilities are identified and addressed before attackers can exploit them. These audits include scanning code for insecure patterns, testing user input fields for weaknesses, and reviewing permissions for scripts and other content. Proactively catching issues through audits prevents small vulnerabilities from growing into major breaches, helping developers stay one step ahead of attackers. Cross-site scripting vulnerabilities may seem like small cracks in a website's armor, but they can quickly escalate into severe breaches. By identifying how these attacks occur and implementing strategies like input validation, encoding, and CSPs, developers can protect both users and applications from harm. Every click you make online carries a layer of trust. But what happens when that trust is exploited? Well, cross-site request forgery or CSRF attacks thrive on this vulnerability, making them a critical threat to understand and mitigate. In this video, we'll analyze a CSRF attack. What does a CSRF attack involve? Let's begin by understanding how this type of attack works. CSRF attacks occur when attackers embed malicious requests into trusted websites, emails, or other content. These attacks exploit a logged-in user's active sessions by making unauthorized requests on their behalf. For example, imagine receiving an email with a link that secretly transfers money from your bank account when clicked. The trick lies in your browser's trust. When you're logged into a website, your browser automatically includes your session token with requests. This token, while convenient for seamless browsing, becomes the gateway for attackers to execute unauthorized actions without your knowledge or consent. Now that we've introduced CSRF attacks, let's explore how attackers exploit active user sessions to perform unauthorized actions. In 2012, a CSRF vulnerability was discovered in GitHub, a widely used platform for developers. Attackers leveraged this flaw to exploit logged-in users by tricking them into visiting malicious websites. The vulnerability allowed unauthorized actions to occur on behalf of the victims, such as adding unauthorized SSH keys to their accounts. This worked because GitHub relied on session cookies to verify users, but didn't implement the right safeguard. If a user with an active GitHub session was tricked into clicking a malicious link, the request was processed as if it came directly from the user, bypassing authentication. Understanding how attackers exploit vulnerabilities leads us to consider the real-world consequences of CSRF attacks. In the GitHub case, the consequences were severe, By exploiting the vulnerability, attackers could add unauthorized SSH keys to user accounts. This gives them access to repositories, potentially exposing sensitive code, proprietary information, or personal projects. For developers and organizations, this could result in data theft, intellectual property loss, and reputational damage. For users, CSRF attacks can lead to a range of unauthorized actions, such as password changes, funds transfers, or exposure of private data. The stress and financial losses caused by these attacks can have lasting effects. For organizations, the damage extends beyond financial loss. Security breaches erode user trust and can lead to customer attrition or even legal consequences. With the consequences in mind, it's critical to examine how systems can be protected against CSRF attacks. Organizations use several key strategies to protect against CSRF attacks, each designed to ensure that only legitimate requests are processed. One effective method is implementing CSRF tokens. These are unique, session-specific values included with forms or requests to verify their authenticity. Since the tokens are tied to the user's session and generated by the server, attackers can't forge them. If a request doesn't include a valid token, the server rejects it outright. In GitHub's case, implementing CSRF tokens, a well-established technique in 2012, would have directly prevented the attack. Another important strategy is using same-site cookies. These restrict cookies from being sent with cross-site requests, ensuring that cookies are only included with requests originating from the same domain. This prevents attackers from exploiting active sessions through malicious external links. Although same-site cookies were introduced later, they represent a critical layer of defense that modern applications should adopt. By combining CSRF tokens and same-site cookies, organizations can significantly reduce the risk of CSRF attacks. Together, these techniques form a robust defense, safeguarding user sessions and fortifying web applications against unauthorized requests. CSRF attacks exploit trust to turn innocent users into malicious actors. However, strategies like CSRF tokens and same-site cookies can fortify systems and block these attacks. By understanding how CSRF works, developers can build safer web environments and protect users from harm.
In this screencast, we're going to demonstrate how to implement and test expiration policies using iMemory Cache and Redis in .NET. We have three separate methods to show three different approaches to managing cache expiration. The first is to use set options to specify an absolute expiration in iMemory Cache, that object. The second is to implement logic to reset expiration with access. And then the third method will show how Redis dependencies can trigger cache updates. So let's look at the first method. We've got our absolute expiration here, and we'll look at the cache absolute method. The first thing we're doing is using a memory cache, which is a library that we can use just to set an in-memory cache for our cache options. We're going to set a key, which is absolute key, and a value, which is cache data with absolute expiration. This is the key value pair that we're going to pass into the cache and store in the cache. These are just two string values. Then we're going to create a new object, memory cache entry options, and set that to the variable cache entry options. And we're setting an expiration of 5 seconds. So that's our absolute expiration. You can see that property .set absolute expiration, which means when that 5 seconds expires, then the cache expires. There's no reset. The data in the cache is deleted. So then we set our cache to the key value pair plus the expiration, the cache entry options, and we write out to the terminal. Our value is going to be written out based on the key that we pass in. The next line just will sleep for 6 seconds, which is after the time span that we set for the cache expiration, so the cache should have expired by then. And then we're going to write out what we see after the expiration happens. Either we're going to see the cache value, which should be this line, cache data with absolute expiration. If it has expired, then we should see cache expired. So I'm going to go ahead and run this. So we see that we stored that value in our key value pair, cache data with absolute expiration. And then after expiration, we see that the cache indeed has expired, which is what we expect. All right, let's look at our second method. This is a sliding cache. A sliding cache we're going to set up pretty much the same way. We've got the key value pair But instead of using the absolute expiration, you can see that on the memory cache entry options, we have the dot set sliding expiration, which is 5 seconds. So that will essentially slide the expiration for the cache. As we work through this for next loop, it goes through 3 seconds, pauses for 4 seconds in the middle. After the loop is finished, then we'll sleep for another 6 seconds, which is after the 5 seconds we set for the sliding expiration. And then we'll write out whether we either can get the value from the cache or whether the cache expired. We should be able to get the cache each time we go through the loop because we have set that sliding expiration on the cache. So I'm going to comment out the absolute cache method and run the sliding method. All right, so the first time through the loop, we see our string cache data with sliding expiration. Same thing the second time through and third time through. Wait for 6 seconds, and now after the expiration, we see that the cache indeed has expired. So we're able to get that data from the cache for those 3 times through the loop, and then it expires after the loop's complete. Now the third method is using Redis. So here we're going to use a Redis database to store items in the cache. We have 2 items we're going to put in the cache. That's set by db string set async. We have a parent key, which is product, and then a child key, which is inventory. For the parent key, we're going to insert product data for that cache item. For the child key, we're going to insert inventory data. And we're going to write those out just to show that we have them in the cache. And you can see we're calling db string get async and passing in that key. And that's going to return whatever the cache is holding. Then we're going to update the parent. So we have db string set async parent key again, and we're going to insert for that parent key updated product data. The next line, the if, will nullify what the child key, and you can see if the string get async parent key equals a certain value. On that child key item that's in the cache, we're going to delete that child key. We can actually invalidate the child based on an update to the parent. The state check will write out to the console what the parent is, and then we're going to try to get the value of the child key. In this construct here, if the child key does have a value, we'll see what's in the child key, otherwise it should return cache expired. Now, based on how we're using Redis in this context, we should see cache expired because we're removing it, we're deleting that key when the parent gets updated. So I'm going to comment out my second method and uncomment the Redis method. I'll go back down here and let me clear out my terminal. And now when we run this, we have the parent and the child both added to the Redis database. When we update the parent, we're expiring the dependent entry, which is our child entry. We've updated the parent with updated product data, so that's the new string that we added to the parent item. And when it tries to retrieve data for the child, you can see that the cache is expired, which is what we'd expect down here because we have deleted that item. In this screencast, we can see 3 different ways that we can implement cache expiration in the .NET framework, and each context or each approach has different purposes depending on what you're trying to accomplish in your app.
Mastering the identification and mitigation of web application vulnerabilities is critical to ensuring secure and reliable systems. Gaining insights into threats like SQL injection, XSS, and CSRF equips you with the knowledge to protect your application and users from potential attacks. We began by exploring foundational web application vulnerabilities, providing essential insights into the threats that jeopardize application security. Next, we explored SQL injection, examining how attackers exploit this vulnerability to manipulate databases and the significant impact it can have on web applications. Then, we analyzed cross-site scripting, or XSS, investigating how harmful scripts can compromise users and interfere with application functionality. After that, we focused on cross-site request forgery, or CSRF, examining how this attack exploits user authentication to carry out unauthorized actions. And finally, we examined real-world examples of these vulnerabilities, identifying effective strategies and tools to mitigate risks and enhance application security. As you've discovered, understanding common web application vulnerabilities is essential to building secure systems. By examining threats like SQL injection, XSS, and CSRF, you've gained valuable insights into how these attacks work and how to defend against them effectively. Welcome to Secure Coding Practices and Input Validation. Here we will explore key techniques for strengthening application security, such as input validation, encoding, and secure data handling. By the end, you'll be ready to implement best practices to protect your application and data. We will begin by exploring secure coding practices, focusing on foundational practices that help prevent vulnerabilities and strengthen application security. Next, we will examine input validation, examining techniques to ensure that user-provided data is verified and processed safely to protect applications from malicious inputs. Then, we will develop encoding and sanitization techniques and build an understanding of their critical role in neutralizing potentially harmful data and maintaining application integrity. After that, we will focus on secure authentication and authorization, exploring best practices to safeguard user access and protect sensitive resources effectively. Finally, we will address secure data storage and transmission techniques, discovering strategies to protect data at rest and in transit, ensuring its confidentiality and integrity. By the end of this module, you'll have the skills to implement secure coding practices and protect your application and data from vulnerabilities. Let's begin. Every time you use an app, shop online, or share data, you are trusting the software to protect you from threats. Secure coding principles are the foundation for building systems that minimize vulnerabilities and safeguard that trust. In this video, we'll define key secure coding principles that minimize vulnerabilities. The first step in secure coding is reducing the ways an attacker can access your system. These entry points include any feature or connection that allows external access, such as an API, open port, or service. The attack surface refers to the total number of entry points available for an attacker to exploit. A larger attack surface means more opportunities for vulnerabilities. By minimizing it, you make applications safer. To minimize the attack surface, start by identifying and disabling unnecessary entry points, such as unused APIs or open ports. Additionally, remove any features that are not essential to your system's functionality. By doing so, you reduce the number of potential vulnerabilities attackers can exploit. For example, a blog site where users don't need to upload files can remove the file upload feature, reducing the risk of attacks. By limiting entry points, you reduce the number of places attackers can exploit, making your systems harder to breach. Once you've minimized the attack surface, the next step is controlling what users and processes can do within your system. This is where the principle of least privileges comes in. Least privileges ensures users and processes have only access they need to perform their tasks, and nothing more. This minimizes the damage that could occur if an account or system is compromised. Assign roles that grant just enough access for users or processes to complete their tasks. Review and update these permissions regularly. For instance, a support team may only need read-only access to customer data, while database administrators require permissions to update it. By restricting support accounts to view-only access, you protect data integrity and reduce risk. Controlling access reduces the impact of a breach if an account is compromised. Even with strong access controls, errors can still happen, and it's critical to design systems to default to a secure state when things go wrong. Fail securely ensures that when a system encounters an error, it defaults to a secure state, avoiding the exposure of sensitive information or the introduction of new vulnerabilities. To fail securely, design your system to handle errors by implementing secure fallback mechanisms. Additionally, ensure that error messages do not reveal sensitive details that could be exploited by attackers. This approach helps maintain security even when things go wrong. Consider a login system that locks accounts after multiple failed attempts and shows only generic error messages. This prevents attackers from learning details about the account while still protecting the user. By failing securely, you maintain system safety even during unexpected events. Guarding against errors is essential, but you also need to protect your system from harmful data. This is where input validation becomes critical. Input validation is the process of checking user inputs to ensure they are safe, accurate, and free of harmful or unexpected data before allowing further processing. To validate input, establish clear validation rules that define the type and format of data your application accepts. Ensure these rules are applied consistently across your entire system to effectively prevent harmful or unexpected data from being processed. Think of a feedback form that only allows text in its comment fields. By rejecting any input outside the expected format, you block harmful code before it reaches your system's core processes. Validating input ensures that harmful data is stopped at the source. Secure coding practices are the foundation of software that stands strong against vulnerabilities. By applying these principles, you're not just writing code, you're building trust, reliability, and safety into every system you create. Building secure software doesn't happen by chance. It requires careful planning and consistent practices. The Secure Development Lifecycle, or SDL, provides a structured approach for integrating security into each stage of software development. It ensures that applications are designed, built, and maintained to resist evolving threats. In this video, we'll describe the steps in a Secure Development Lifecycle, or SDL. SDL is a structured process that integrates security at every stage of software development. It starts with planning to identify and mitigate risks early and continues through development, deployment, and maintenance to ensure systems remain protected against evolving threats. The first step in the SDL is designing your software with security as the top priority. During the design phase, developers identify potential risks and create plans to address them before writing any code. For example, when planning a login system, a developer might decide to include multi-factor authentication. This ensures that even if a user's password is compromised, their account is still protected by an additional layer of security. By proactively considering security during design, developers can minimize vulnerabilities from the start. The second step is to ensure the code itself is secure through regular code reviews. Code reviews are evaluations of code by other developers to ensure it meets quality standards and adheres to best practices. For instance, a reviewer might catch an exposed API key in the code and recommend replacing it with a secure method to prevent unauthorized access. By reviewing code regularly, teams can find and fix issues before they become real problems, strengthening the overall security of the application. The final step in the SDL is continuous improvement. Security isn't a one-time task. It's an ongoing process to stay ahead of new and evolving threats. For example, if a team learns about a new phishing technique, they might update their email verification system to block suspicious links. By continually refining and improving their application, developers can ensure it remains secure over time. Let's take the example of building a secure e-commerce website. During the design phase, the team plans to secure payment processing by using encryption and enabling multi-factor authentication for user accounts. Once development begins, they conduct regular code reviews, catching issues like hard-coded sensitive information and replacing it with secure environment variables. After deployment, the team commits to continuous improvement by monitoring emerging threats, such as new vulnerabilities in payment processing libraries, and promptly applying patches and updates. This end-to-end approach ensures the website stays secure through design, development, and ongoing maintenance. Security is a continuous effort, not a single event. By following the steps of secure development life cycles, designing with security in mind, conducting regular code reviews, and committing to continuous improvement, developers can create a cycle of protection that safeguards software from design to deployment and beyond. Whenever you submit a form, create an account, or place an order on a website, the data you enter goes through checks to ensure it's correct and safe. These checks are called input validation, and they play a key role in keeping applications both user-friendly and secure. In this video, we'll describe the differences between client-side and server-side validation. Let's start with client-side validation. Client-side validation happens directly in the user's browser, providing immediate feedback before the data is sent to the server. This approach is great for improving the user experience by catching simple mistakes early. Imagine filling out an email field. If you forget to include the @ symbol, client-side validation will instantly display an error message letting you fix the issue before submitting the form. While client-side validation enhances usability, it can be bypassed. Someone can disable browser checks or manipulate the data using malicious tools. And that's where server-side validation comes in. Server-side validation occurs on the server after the data is submitted. It enforces strict checks to ensure security and proper functionality. Server-side validation is essential because it cannot be bypassed by the user. When you create a new account, the server checks whether the username entered is unique. This ensures there are no duplicates and that the system functions as expected. Next, let's discuss allow lists and block listing, two strategies for filtering inputs. Allow list validation permits only pre-approved expected inputs. By explicitly defining what is allowed, it reduces the risk of harmful or unexpected entries. For example, in a username field, allow lists can restrict inputs to only letters and numbers. This prevents special characters or symbols, which could otherwise cause errors or be used for malicious purposes. Allow listing is particularly effective for critical inputs, and it ensures strict control over what is accepted. Now let's discuss block list validation. Block list validation prevents inputs that are known to be harmful or suspicious. It works by identifying and blocking specific inputs or patterns, such as malicious SQL commands. For instance, if someone tries to submit a harmful SQL command, like drop table, block list validation can detect and block it to protect the database. However, block listing is less reliable than allow listing because it relies on identifying known threats. Attackers can create new, unexpected inputs that bypass the block list. For this reason, block listing is often used as an additional layer of defense rather than the primary validation method. Input validation does more than catch user mistakes. It's a critical defense layer against malicious activity. By understanding client-side and server-side validation and when to use allow listing and block listing, you can ensure your web applications are both secure and user-friendly.
When you're creating web applications, validating user input can be very important. It can make sure that the data that you're collecting is the data that you want to collect in the right format. And this is really important as you think about managing data and then processing it. In this screencast, we're going to look at validating data both on the server side and the client side with just two very simple applications, the client and the server. In this project, I do have a client app with the index.html and a validation.js, which is going to do the validation work. And then I have a server side, the node server with server.js in it. Let's start by looking at the client side and how this client application will validate information coming into it. All the validation is done on the client side. In this HTML file, it's very simple. It's a form. It has an email field and a username field. It's referencing validation.js, which will actually do the validation when the form is submitted. So the user will enter information, and then when they hit submit, it will run the logic inside of validation.js. In validation.js, we have an event listener for the submit event. And when that happens, the email and username field will be populated from the data that's in the form on the HTML side using document.getElementById. This is where we do the validation. We're checking that the email includes the @ symbol. If it does not include the @ symbol, it will produce an alert that the format's invalid. And if it does, then it will submit the form as normal. Now, there's no logic in here to submit the form. It would move past that if statement and do whatever else we wanted to do with that data. Notice also, too, we're checking that the username length is at least 3 characters. So if it's less than 3, then we inform the user that the username must be at least 3 characters. So let's go ahead and test that. I'm going to click User HTML. I'm going to use a preview extension in Visual Studio Code that will allow us to see things in the browser. So I'm going to start by just putting in invalid data. So I've got a 1-character username and an email that doesn't have an @ symbol in it. I'll click submit, and it says please include @ in the email address. Foo is missing an @. Now I'm going to take this out and submit again. And you'll notice that it's also saying that the field is required. That's because in our index.html, we have more validation where we're asking it to make sure that the field is required and that it's being used properly. So let's go back to our browser. We'll put in a valid email address. And then I'll put in a username that's correct. And when I click submit, it submits it fine. Now, if I do a valid email address, but an invalid username, it will tell me with an error message that the username must be at least 3 characters long. So all the validation works. The fields are required. We have to have a username that's at least 3 characters and a valid email address format. So that's validation on the client side. We can also validate on the server side. So I'm going to go to the server. And here's the entire application where we're creating a post route. So we're going to submit, again, email and username. It's going to do the same validations. The username has to be at least 3 characters long. The email has to include an @ symbol. Otherwise, it'll produce an error. Now, there's no user interface here because you can imagine servers where there's a web browser and the person is filling out a form and it sends it to the server as a package from the browser. And it's just all data coming into the server. But it will produce errors, and then those errors can be sent back to whatever client is trying to submit that data. So we're going to use a tool called Postman, which simulates sending a package of data to a server. And when that package comes into the submit route, we're going to parse the email and username. We're creating an errors variable to hold any errors that might occur. And then we do our checks. We have these if statements that checks to see if there's something wrong. On line 15, if an error is produced, in other words, the length of the error variable is greater than 0, then we're going to return a status 400 and show the JSON errors. Otherwise, return a status of 200 and let the calling, whatever it is, in this case Postman, the calling application or the calling form, let them know that the form was submitted without errors. So I'm going to go ahead and run my application. This is just a simple node server. So now that the server is running, we can make post requests to the server. So I've got the localhost with the port number of 3000, which is what is running on the server side. The server is running on port 3000. So we're going to send our package to that. And we're sending in our package as a JSON entity. So we have an email with the email of Foo and a username of Joseph. So let's go ahead and try to send that, and we should get a response back from the server. We get an error, and that's what the server would send back to whatever called it. We can call it from any application or website or whatever, and the error is going to come back in valid email format. And then in the calling application, we can take that feedback from the API call, and then we can do something with it. We can inform the user or ask them to try again or whatever. Now let's go ahead and put in a valid email address. And again, we're just checking for the @ symbol here. There's lots of things you can check. You can add code to your server to check for a dot. You can make sure that the email is of a specific length. You can check anything you'd like. This simple example is just checking for one thing. So, okay, now we'll go ahead and resend that, and we'll see what it comes back with. And it tells us that our form was submitted successfully because we met all the requirements. We have an @ symbol, our email address, and our username was longer than 3. So let's make our username now just 1 character, and we'll see what the server comes back with. And there's our error again. Username must be at least 3 characters long. So we have that in our error variable. Now I'm going to take out the @ symbol from this and click send one more time. The error was an array. It's in brackets, which means it can hold more than one error. So in this case, the error came back that the email format was invalid and the username must be at least 3 characters long. So if we were taking this on our client side, we would have to tell the user that there were 2 issues and that the email format was wrong and that their username was too short. And we can do that in our client app. So this is an example of how you can validate input from users from the client side. You can show it on the client side. and you can also show it on the server side. If you're collecting data, it's generally best to do the validation on the server side and then send that back to the client so that the client can process that and do something with it if you're making API calls that you want to submit data. A lot of developers will try to catch those things on the client side so it never actually gets to the server, which can save an API call. That's also a good practice if you don't want to have the data go to the server. The only gotcha there is that sometimes people can get around validation on the client side. So you have to be careful to make sure that you're not getting spoofed or anything like that. A good practice would be to do it on both. And make sure that you're validating the data before it gets to the API call. If it gets past the client, then make sure you're also validating it on the server side. And this is an example of how you can do both. In this lab, we're going to implement input validation in a sample web application to ensure secure handling of user inputs. We're going to have a client-side version and a server-side version. So in step one, we're going to set up the client-side validation. This is going to provide immediate feedback to users using this form to let them know that there's certain fields that aren't valid for what we need in terms of data. And this will happen before data is ever sent to the server. So we can catch it before the server has to process information or we have to make an API call. So in this HTML page, we've got our head with some header information. And then in our body, we have an H2 and then our form. So here's where all the validation is going to be done. You can see we have required on these two fields, the name and the email. The feedback also message is required. And then we have our submit button. Now in our script, we're going to do some more work here to validate the input. So we create three variables, name, email, and message, and we're just going to grab those from the elements in our form, name, email, and message, same exact name. And we're going to trim off any spaces on either side of that so we don't have any extra spaces. And then we have three if statements. We're going to check whether the first field has a valid length by calling the isValidLength function. And if not, then we're going to produce an alert that the name must be at least 3 characters long. We're going to do the same for the email. So we're going to have an isValidEmail function that will check that email. And then we're going to check the length for the message. The message must be at least 10 and less than 200 characters in length for that message to be valid. We're going to check these. If any of them is not appropriate, the user will receive a message and they won't be able to submit the form. In step 2, we're going to look at server-side validations. If the user submits this form and everything looks right on the client side, we want to be able to catch anything on the server side in case something's been spoofed or some error has occurred and the client-side validation didn't catch it. We now have a second line of defense on the server side. In step 2, we'll implement server-side validation. We have our post route here, which is validate. So when this form is submitted, it would go to this validate before it goes and moves on to the next step, which might be storing it in a database or doing something with it on the server side. So again, here we're passing in to the request, the name, email, and message, which came from our form. And then we've got 3 if statements here. So on the if side, is valid length, is valid email, and is valid length again for the name, email, and message. If we're going to call these functions, is valid length, is valid email, and is valid length, we're going to call these functions if the return value is negative. So we're using that exclamation point. So if is valid length returns false, essentially, is valid email returns false, is valid length returns false, we're going to produce this message. We're going to push this message as a part of our response. And we're going to let the user know that they could not submit the form. We do have those functions here, is valid length and is valid email. So that's what this server code will be calling, is those other methods that we have in our server-side application. So these are 2 ways that we can validate user input, both on the client side and the server side. And it's good to have validation on both. One, so that the user doesn't waste their time submitting invalid data, then have to refill it in, waiting for the API call to complete. And two, we want to make sure that we're getting the right data that we need in our database. So ensuring that we have valid data on both sides will keep our data clear, and we won't have to run any post-processing on that data once it's in the database.
Every piece of user input in a web application is a potential gateway for attackers. Encoding protects against this by transforming user input into harmless data, shutting the door on injection attacks before they can even begin. In this video, we'll describe the role of encoding in preventing injection attacks. Encoding protects different parts of an application in specific ways. HTML for displayed content, JavaScript for scripting, and URL encoding for links. Let's start with HTML. HTML encoding converts potentially harmful characters into safe versions that a browser will treat as plain text. This ensures that user-submitted content cannot disrupt the page or run harmful commands. Imagine a user submits a string containing script with alert hacked. Without HTML encoding, the browser might interpret this as actual code and execute it, showing a pop-up. With HTML encoding, the left angle bracket and right angle bracket symbols are converted into their safe equivalents, &LT and &GT. The input is displayed as plain text instead of running as a script, keeping the page safe. Next, let's explore how JavaScript encoding prevents harmful scripts from running in their application. JavaScript encoding protects your application by neutralizing characters that could trigger harmful scripts. It ensures that user input is treated as text and not as part of a script. Suppose an attacker submits inputs with quotes or characters intended to break a script, like double quote, semicolon, alert hacked, semicolon, //. Without encoding, this input might execute within your application. JavaScript encoding transforms these unsafe characters into harmless representations, ensuring the input is treated as plain text rather than as part of a script. This keeps both your users and your application safe. Finally, let's explore URL encoding, which ensures that links and search queries remain safe and properly formatted. URL encoding converts special characters in URLs, like spaces, slashes, or symbols, into safe representations so they are interpreted correctly and securely. This prevents attackers from manipulating links or injecting harmful characters into URLs. Consider a URL that includes search parameters. If a user submits unsafe input like a space or special symbol, the URL might break or be misinterpreted. With URL encoding, spaces are converted to %20 and other unsafe characters are transformed into their safe equivalent similarly. This ensures the URL remains functional and secure. For instance, example.com/search ?query equals hello world becomes example.com/search ?query equals hello $20 world. URL encoding guarantees that links and search queries work as intended without creating vulnerabilities. Encoding is one of the simplest yet most effective techniques for stopping injection attacking. By using HTML encoding, JavaScript encoding, and URL encoding, you can transform potentially harmful inputs into safe, reliable data. This approach protects both your application and its users, ensuring that inputs are always handled securely in different contexts. When user input isn't handled carefully, it can open the door to attacks that compromise your web applications and its users. For example, malicious scripts might be injected into your web pages if input is not treated properly. Encoding solves this problem by transforming potentially dangerous input into harmless plain text. In this video, we'll apply encoding techniques in a web application. To demonstrate encoding in action, we'll build a small project that encodes user input before displaying it on a web page. The project consists of a basic HTML form that users can enter text and a JavaScript function that processes and encodes the input, ensuring the data is safely rendered in the browser. Before writing the code, let's set up the project environment. Start by creating a new folder for the project and giving it a name. Open the folder in Visual Studio Code. Inside it, create one file named index.html, which will contain both the front-end structure and the JavaScript functionality. We'll create a simple HTML form that allows the user to enter input and displays the result. The key here is to encode the input so it is displayed as plain text, not as executable code. Go to your index.html file, start by generating the basic HTML structure using a shortcut. Type exclamation point into the file and press enter. This will produce a clean starting template that includes the document type declaration, character encoding, and a title. Inside the body section, create a headline using an H1 tag for the title and a subtitle using P tags. In the subtitle, write characters like left angle bracket and right angle bracket as &LT and &GT respectively, to use safe encoding. Next, create a text input field where the user can type something. Use the input tag and add the attribute type equals text to specify that it's a text box. Include ID equals user input to make the input accessible later with JavaScript. To guide the user, set the placeholder equals enter text. Now, we need to add a button that triggers a JavaScript function when clicked. Use the button tag and include the onClick attribute to specify the function to run. Set the attribute to onClick equals handle input and remember the parentheses, which will call the handle input function when the button is clicked. For the button's label, use the text submit so it clearly tells the user what action to take. Below the button, add a div to serve as the output area where the processed input will be displayed. Style the div with white space. Pre-wrap to ensure that any text, including spaces and line breaks, is displayed exactly as it is. Use font family monospace to neatly align the text. The ID equals output gives us a way to target this area and update its content using JavaScript. At this point, the basic interface is ready, but clicking the button does nothing yet. To make it functional, let's add JavaScript. Open a script tag at the bottom of the body and create the handle input function. The handle input function begins by retrieving the value the user typed into the input field. To do this, we use document.getElementById with the string user input, then .value, and store the value in a variable called input. Next, a temporary div is created using document.createElement with the string div. This div acts as a helper to safely encode the input. By assigning the raw input to tempdiv.textContent, the browser ensures that any special characters like left angle bracket and right angle bracket are treated as plain text and not HTML. After encoding the input safely, we target the div with ID equals output and update its content. The line output.textContent equals tempdiv.textContent ensures that the encoded text is displayed in the output area as plain text. Save the file and open it in your browser. If you're using Visual Studio Code, right-click the index.html file in the Explorer panel and select Open with Live Server. This will launch the file in your default browser. Let's test the application by entering script alert XSS and then close that script tag into the input field and clicking the submit button. Instead of executing the script or causing any harm, the browser should safely display the input as plain text in the output area. This happens because the function encodes the input using text content, which transforms potentially dangerous characters like left angle bracket and right angle bracket into harmless text. As a result, the browser treats the input as plain text, preventing it from being interpreted or executed as code. By encoding the input this way, it can be safely rendered in the DOM without risking any attacks or compromising the browser. This simple yet effective approach ensures that even if a user submits potentially malicious content, your application remains secure. Every user input is a potential risk, but encoding techniques give you the tools to turn that risk into safety. By mastering HTML encoding, you're taking a vital step towards building secure web applications. Every piece of user input in a web application is a potential entry point for attackers. Without proper sanitization, seemingly harmless text can transform into malicious scripts, compromising both the user and the application. In this video, we'll explain how sanitization prevents cross-site scripting attacks by removing dangerous inputs. To defend against these threats, developers rely on sanitization. Sanitization is the process of cleaning user inputs to remove potentially dangerous content, preventing attacks like cross-site scripting where malicious scripts are injected into websites. Attackers often embed harmful HTML tags such as script tags to execute malicious code. Sanitization removes these tags to ensure inputs remain safe. Imagine a review form on a shopping website. A malicious user could submit a comment with a hidden instruction to redirect visitors to a dangerous site. By stripping harmful tags like a script tag, sanitization ensures the input is treated as plain text, eliminating the risk. Manually checking and cleaning every user input can be time-consuming and prone to mistakes. Sanitization libraries automate this process, ensuring consistency and efficiency. DOM Purify is an open-source JavaScript project that cleans HTML to protect against cross-site scripting attacks. It scans user inputs and removes or neutralizes dangerous content, making them safe for use in web applications. Think of a comment section on a blog. DOM Purify can automatically scan the submitted comment, strip harmful scripts, and allow only safe content. By using tools like DOM Purify, developers reduce the risk of vulnerabilities without manual effort. User inputs can appear in different parts of a web application, such as HTML, CSS, or JavaScript, and each context requires specific sanitization rules to address its unique risks. For instance, in HTML, sanitization ensures that only safe tags, like a B for bold text, are allowed while removing risky ones, such as scripts. This is particularly useful in fields like product descriptions, where only specific formatting tags should be permitted. In CSS, attackers might attempt to inject harmful styles, such as using the background image property to load unsafe content. Proper sanitization prevents this by allowing only safe CSS properties, effectively blocking malicious URLs hidden in styles. For JavaScript, inputs used in dynamic features like search bars require special attention. Here, sanitization neutralizes any input to ensure malicious scripts cannot execute, which is essential for preventing attacks that exploit interactive elements. By tailoring sanitization rules to the specific context, whether HTML, CSS, or JavaScript, developers can safeguard every part of the application and reduce the risk of vulnerabilities. Sanitization transforms risky inputs into safe ones, acting as a crucial barrier against cross-site scripting attacks. By applying these techniques, developers protect their applications and users from unseen threats, ensuring a secure and trusted experience.
Managing security on your website will help make your data and your users more safe. In this lab, we're going to implement encoding and sanitation techniques to prevent cross-site scripting or XSS attacks in a sample web application. In step 1, we're going to implement HTML encoding. I've got a simple node.js website here in Visual Studio Code. And this website has a simple input form. So you can imagine this is a place where users can enter comments. So we have an input field called user input, a button where they can submit the form, and then a div that displays any output. When the user clicks the button, it runs this process input function. And we're going to do 3 different things in this function. But for this one, we're going to concentrate on this first section. The first thing we do is grab the input from the user input field up here at the top. We're placing it in the value input. And then the first thing we're going to do is encode any HTML. That means rendering any HTML tags as plain text. By encoding it, the HTML becomes less dangerous. It just becomes a text field rather than actual HTML when we render it to the screen. How we're going to do that is to take that input and we're going to create a temp div, which is essentially a div element that we're going to hold in memory. And then we're going to assign the input value to that div element, but we're going to use this text content property. By using the text content property, it just renders whatever's in that input to text. So it essentially encodes it for us by using that property. Once it's encoded, then we can also output it, so we can get the output element and also set its text content property to the tempdiv.textContent. The way that we're encoding this is by using that text content property, so we don't have to do any manual encoding. In step 2, we're going to implement JavaScript encoding. And we're going to use regex to do that. So again, we're taking that input that we're grabbing here at the beginning of the function. We're assigning that to safe input, but we're going to use this replace function to go through and look for any code that we don't believe is safe. And we're going to put a slash in front of it. It's called escaping characters. So we can escape it so that it renders it as text in the output rather than displaying it as anything that could cause harm, like a script or any HTML that we don't want it to render. By using that replace with regex, we can escape anything that we want to escape there, and then the output will be rendered safe. The third thing we're going to do is in step 3, implement URL encoding. So here we're going to encode any URL elements, so they are also rendered safe. We're taking that input variable again, and we're going to use this encode URI component function against the input and assign it to encoded URL. So that function will do all the work that we need it to do for us to encode that URL that's being passed in, if there is one. And then we're just going to put output to the console in the browser, the encoded URL using that variable. So these are 3 different ways that we can encode different aspects of whatever the user happens to pass in. In a real-world application, you might run the input through all 3 of these so it catches any elements that you want to catch before using that input in any data manipulation or even putting it to the browser. In step 4, we're going to implement input sanitation with a library called DOM Purify. And DOM Purify will do a lot of work for you. So some of these items you don't have to do manually. We brought in DOM Purify in the header using the script tag. So this is a complete library that will clean up any inputs that you have. So here we're using that input variable again at the top that we're setting here. And we're going to call dompurify.sanitize. So it's a single function call that will go through and sanitize your input for you, removing anything dangerous. We're going to assign that to sanitized input and then output the contents of that variable to the log. Sometimes DOM Purify may remove too much or doesn't give you some visibility into the things that you want to have control over. So sometimes you want to do some of this work manually like we've done in step 1 through 3. But if you don't, if you just want to make sure that your input is clean and safe, DOM Purify is a great library to do that work for you. So these are 4 different ways that you can approach content and inputs on your website to make sure those inputs are safe and won't harm your data or your users.
In today's digital world, protecting user accounts is more critical than ever. From creating strong passwords to integrating advanced authentication methods, mastering these techniques is essential for building secure and trustworthy systems. In this video, we'll describe the core techniques for secure authentication and their importance. The foundation of secure authentication starts with strong passwords. But how can we ensure users create passwords that truly protect their accounts? A password policy is a set of rules designed to enforce secure password practices. These rules typically include requirements for password length, complexity, and periodic updates. For instance, a robust password policy might require passwords to be at least 12 characters long and include uppercase and lowercase letters, special symbols, and numbers. Additionally, it might enforce expiration every 90 days, reducing the risk of vulnerabilities from reused or compromised passwords. Password policies create a first line of defense against unauthorized access. Passwords alone aren't enough to fully protect accounts from modern threats. And that's where multi-factor authentication, or MFA, comes in, adding an essential second layer of security. Multi-factor authentication requires users to verify their identity using 2 or more independent factors. This combines something you know, like a password, with something you have, like a phone-generated code. Consider logging into a bank app. After entering your password, you're prompted to enter a one-time code sent to your phone. Even if someone steals your password, they can't access your account without the second factor. MFA dramatically reduces the risk of unauthorized access, even if passwords are compromised. While MFA improves account security, there's another way to enhance both security and convenience, using trusted third-party accounts through OAuth. OAuth is a secure protocol that allows users to log into applications using accounts from trusted providers like Google or Microsoft. This eliminates the need to create new passwords, reducing the risk of weak or reused passwords. Imagine signing up for a fitness app. Instead of creating a new password, you can select Login with Microsoft. OAuth ensures your account is linked securely while minimizing the number of credentials that you need to manage. OAuth simplifies login processes, and OpenID Connect takes it a step further by verifying who is accessing the application. OpenID Connect is an identity layer built on top of OAuth. It not only authorizes the user to access an application, but also confirms their identity by providing an ID token. This token includes details like the user's name or email address, which the application can trust because it's signed by the provider, for example, Google or Microsoft. When you log in to an app using your Microsoft account, OpenID Connect ensures it's really you by verifying your credentials and providing the app with your identity information. This extra layer of verification helps prevent impersonation and ensures only you can access your account. OpenID Connect combines security and usability by enabling applications to confirm who is logging in without requiring complex extra processes or extra steps for the user. This makes authentication both seamless and highly secure. Effective authentication is about more than just security. It's about creating a seamless experience for your users. By implementing strong password policies, multi-factor authentication, and OAuth and OpenID Connect, you can safeguard sensitive data while enhancing user trust and confidence in your applications. In today's digital world, protecting user accounts is more critical than ever. From creating strong passwords to integrating advanced authentication methods, mastering these techniques is essential for building secure and trustworthy systems. In this video, we'll describe the core techniques for secure authentication and their importance. The foundation of secure authentication starts with strong passwords. But how can we ensure users create passwords that truly protect their accounts? A password policy is a set of rules designed to enforce secure password practices. These rules typically include requirements for password length, complexity, and periodic updates. For instance, a robust password policy might require passwords to be at least 12 characters long and include uppercase and lowercase letters, special symbols, and numbers. Additionally, it might enforce expiration every 90 days, reducing the risk of vulnerabilities from reused or compromised passwords. Password policies create a first line of defense against unauthorized access. Passwords alone aren't enough to fully protect accounts from modern threats. And that's where multi-factor authentication, or MFA, comes in, adding an essential second layer of security. Multi-factor authentication requires users to verify their identity using 2 or more independent factors. This combines something you know, like a password, with something you have, like a phone-generated code. Consider logging into a bank app. After entering your password, you're prompted to enter a one-time code sent to your phone. Even if someone steals your password, they can't access your account without the second factor. MFA dramatically reduces the risk of unauthorized access, even if passwords are compromised. While MFA improves account security, there's another way to enhance both security and convenience, using trusted third-party accounts through OAuth. OAuth is a secure protocol that allows users to log into applications using accounts from trusted providers like Google or Microsoft. This eliminates the need to create new passwords, reducing the risk of weak or reused passwords. Imagine signing up for a fitness app. Instead of creating a new password, you can select Login with Microsoft. OAuth ensures your account is linked securely while minimizing the number of credentials that you need to manage. OAuth simplifies login processes, and OpenID Connect takes it a step further by verifying who is accessing the application. OpenID Connect is an identity layer built on top of OAuth. It not only authorizes the user to access an application, but also confirms their identity by providing an ID token. This token includes details like the user's name or email address, which the application can trust because it's signed by the provider, for example, Google or Microsoft. When you log in to an app using your Microsoft account, OpenID Connect ensures it's really you by verifying your credentials and providing the app with your identity information. This extra layer of verification helps prevent impersonation and ensures only you can access your account. OpenID Connect combines security and usability by enabling applications to confirm who is logging in without requiring complex extra processes or extra steps for the user. This makes authentication both seamless and highly secure. Effective authentication is about more than just security. It's about creating a seamless experience for your users. By implementing strong password policies, multi-factor authentication, and OAuth and OpenID Connect, you can safeguard sensitive data while enhancing user trust and confidence in your applications. In today's digital world, unauthorized access can lead to breaches or operational errors. Controlling user access through role-based access control, or RBAC, ensures applications remain secure and efficient by granting users only the access they need. In this video, we'll demonstrate RBAC logic in a web application. Role-based access control, or RBAC, is a security model that restricts access to resources based on user roles. By defining roles such as admin and user and assigning permissions to these roles, we can restrict or grant access to specific actions within the application. To implement RBAC, we will use JWTs. They securely store and transmit user roles and other key details in their payload. This token accompanies each request, ensuring that the user's identity and permissions are validated, forming the backbone of RBAC logic. Now that we understand JWTs, let's define the roles and permissions required for our application. Roles such as admin and user help us structure access. Admins can manage content in users. Users can view content. To implement role-based access control, we store role information within the user object, ensuring that each user's role is clearly defined and accessible for authorization checks. The user object serves as a container for essential data, such as the user's unique identifier, username, password hash, and role, with the latter three being required fields. This structure enables us to assign roles like admin or user to individual users. However, assigning roles is only the first part. Roles need clear definitions and enforceable rules within the application. This is where authorization policies come into play. Defining policies is crucial for structuring access control. These policies will map roles to specific permissions, forming the core of RBAC logic. For instance, we can use the add authorization method to configure role-based authorization and the add policy method to define policies like admin only, requiring the admin role, and user only, requiring the user role. These policies establish clear access controls, ensuring resources are only accessible to users with the appropriate roles. Once these policies are defined, they can be applied to specific routes in the application to enforce role-based access control. With roles and permissions defined, the next step is to explore middleware, which will enforce RBAC logic. Middleware acts as a checkpoint for every request. It can inspect, modify, or stop a request before reaching the route handler. By adding the app.useAuthorizations middleware to the application pipeline, the system enforces the defined authorization policies. This middleware ensures that each incoming request includes a valid JWT and verifies that the user's role matches the permissions specified by the applied policy. With policies defined, we will implement them for verifying the user's role during requests. For example, when accessing the admin panel, only users with the admin role are authorized. This is achieved by defining a route for the admin panel that enforces the admin-only policy. The route is configured to respond with a welcome message, but only if the request passes the necessary authorization checks. The middleware ensures that the incoming request includes a valid JWT and that the user's role aligns with the admin requirement, restricting access to unauthorized users. Now that the RBAC logic is in place, we can test its functionality using Postman. By including the JWT in the authorization header, we can simulate authenticated requests, starting by creating an HTTP request for the secure admin panel endpoint and add the JWT to the header. The server should grant access, confirming the request is authenticated based on the admin role in the JWT. Next, log in as a user and attempt to access the same endpoint. This time, the server should respond with a 403 message as the user role lacks the required permissions for this route. If the RBAC logic fails, verify the JWT payload includes the correct role. The middleware is applied to the intended route, and the JWT is valid and hasn't expired. Applications need to protect their resources from misuse or errors caused by unrestricted access. By implementing RBAC, you're not just securing your application, you're creating a controlled environment where every user can perform their task safely and efficiently.
In this lab, we're going to implement secure authentication and authorization in a sample web application. So I have a simple node.js web application here, and we're going to do a number of things. We've got some endpoints for registration, for login, for sending in a one-time password, and for verifying a one-time password. And then finally, we've got an authorized endpoint and the ability to get information or log into an admin panel. So there's a lot going on here, but we're going to break this down into steps. So in step 1, we're going to set up user registration and login. The first thing we want to do here at the top is bring in all of our libraries. So we've got an Express library, which sets up the web server. And then we're going to use this bcrypt.js library so that we can hash passwords later on. And then we're going to use the JSON Web Token library to be able to set up our tokens so that we can use this login securely. As we go down, we're setting up all our variables. So our app is our Express server, and then we're going to use express.json. We're setting up a user's variable. This is all simulated, and OTP storage variables to store our one-time passwords. And then we've got our first endpoint, our register endpoint, which is a post endpoint because we're going to register a user in the situation. We set up our email and password, which is sent in to the endpoint from the requester. It's a post item, so it's posting information to the endpoint, and we're going to grab whatever's in that body, which is going to be the email and password, and we're going to set our variables to that. We then check the password for the password length. If it's less than 8, then we're going to return an error. Otherwise, we're going to hash our password using the bcrypt hash function. So in this situation, the hashed password is going to be equal to whatever that bcrypt hash returns. So that's why we're using that library, so we don't have to create that hashing function ourselves. We just go ahead and use that bcrypt.hash function. Once we get that password hashed, then we can create the user, and we can send back a message that the user was registered successfully. Our second endpoint is the login endpoint, because now the user has been created. Now we can actually allow them to log in. So again, we do the same thing. We set email and password to whatever they've sent in to log in. We set the user to the email field, and then we use this bcrypt.compare to compare the password with the user password that we've hashed. The user password was passed in. The password is what we are comparing it to. And if they don't compare, if they're not the same, then we would say they have invalid credentials. Otherwise, we're going to create a token using the jwt.sign function. So the JWT was that library that we instantiated earlier. So we're going to use the sign method to create a token based on that email and the user role and the secret that we've created in our env file. So now that we have the token created, we can respond with that token, and that will give the user the ability to sign in securely. So that's step 1, setting up that registration and login. In step 2, we're going to implement multi-factor authentication for our server application. So we've got another endpoint here, app posts send OTP. And OTP stands for one-time password. So if you've ever used a website where they send you a 6-digit code, and then you have to enter that into the website, this is essentially the functionality that does that. A user might request an OTP, a one-time password. It hits this endpoint, and they're going to send in their email to have that one-time password sent to their email. The next line here is to create that one-time password. So we're going to use this function math.floor to do that. We're essentially creating a random 6-digit number using math.floor. So that's an inherent JavaScript function that will create that random 6-digit number for us. We then store the one-time password using the email address as the index for the storage facility that we've set up in this application. We log that to the console, and then we send a message that the one-time password has been sent. In a real-world application, obviously, you would have a facility for emailing that password to the user. In this case, we're just storing it temporarily and sending a message back to the user. The next endpoint is to verify the one-time password. So ostensibly, the user would put their one-time password that we sent them into the application. We would get that in the body of this request. So they would click enter on the website with the email and their one-time password. We can see that we're passing both of these in through the request body. And then we compare if the one-time password that they just passed in on the website is the same as the one we just stored when we created it. Then we can delete the one in the storage because we know that it's valid, and we say that the one-time password was verified. We're going to grant them access and then return that message to them. If it doesn't compare, if it's not the one that we stored in the database, then we tell them that the one-time password was invalid and they can't log in. In step 3, we're going to implement role-based access control, or RBAC. So in this scenario, access to the admin panel should be restricted to admin users only, say. So we're going to use a token to validate that the user is a part of that admin role, and we won't allow them access to the portal unless they are. So the first thing we have here is a function that we're going to use in our endpoint, which we'll look at in a second. And this function is called authorize, and we're passing in a role with a request and a response, and then a next function for the application to move to the next thing that it needs to do. So the first thing we're doing is setting the token to what's been passed in the header, the authorization header for this request. So typically tokens are passed that way as in the authorization header. And we want to pull that out and verify that it's actually present. So if the token isn't in the header, we're not going to allow them access because they clearly don't have the permission to access that resource if they haven't passed in a token. If the token is in the header, then we're going to verify that the user role is what they say they need to be. So we're going to check the user role and use this function JWT verify to verify that the token does contain that role. We have a secret key that we've created, and this is how token-based authentication works. We're going to use our secret key in the verify function so that we can decrypt it and make sure that the token contains the information that we want. If the user role does not equal the role that they're supposed to have to access this resource, then we send back a 403 that the user could not get to that resource. And then it moves to the next function. So that's the function that we are going to use to do the authorization. And the next thing we have here is our endpoint. This is a get method, and the endpoint is /admin. This is to authorize the admin access to that resource. The endpoint is /admin, but we're calling that authorize function with an admin role. That's the role that we're passing in. When we call that function, we want to make sure that the user can't access this resource because they're an admin, which should be a part of that token. Once we called that resource, we pass a value back, either 401, 403, or valid, depending on how the function evaluated that request. Based on the result of that, if it does come back positive, it doesn't send a 401 or 403, then we'll send the user a message back that they're welcome to the admin panel, that we grant them access to that resource because they had an appropriate token. That's implementing role-based access control in our web application. So those are 3 different ways that we can secure access to resources behind API endpoints in a node-based website.
Every piece of data we store, from passwords to payment information, is a potential target for attackers. Encryption transforms this vulnerable information into a shielded asset, keeping it safe even if systems are compromised. In this video, we'll describe how encryption techniques protect sensitive data during storage. Let's start with a widely used encryption method for securing stored data, such as files and records, Advanced Encryption Standard or AES. AES is an industry-standard encryption algorithm that protects stored data by encrypting it in chunks using a secret key. The data becomes unreadable without the correct decryption key, ensuring its security. Imagine a business storing customer purchases with histories. With AES encryption, even if someone accesses the database, the information remains scrambled and unusable without the decryption key. AES ensures sensitive information stays safe from unauthorized access. While AES is ideal for securing files or records, passwords need a different kind of protection called hashing. Hashing is a process that converts passwords into scrambled, fixed-length strings. These strings cannot be easily reversed, ensuring that stored passwords cannot be directly read or stolen. Think about logging into a social media account. When you create a password, it's hashed and stored in a scrambled value. Even if someone breaches the system, only the hash would appear, not your actual password. Hashing alone isn't enough to fully secure passwords. To strengthen it, we use salting. Salt is a random bit of data added to a password before hashing it, ensuring that each resulting hash is unique, even if two users choose the same password. Let's say two users choose password 123 as their password. Without salting, the resulting hashes would be identical, making it easier for attackers to guess. Salting ensures each hash is unique, preventing attackers from using pre-computed rainbow tables to crack them. Beyond securing individual data points like passwords, encryption can also protect entire databases. Let's explore how database encryption works. Database encryption secures sensitive fields, such as credit card numbers, by making them unreadable without a decryption key. This protects the integrity of the entire database, not just individual records. MySQL provides built-in encryption functions that can be used to secure specific fields or tables containing sensitive information. For example, sensitive data like credit card numbers can be encrypted directly within the database using these functions. This ensures that even if unauthorized access occurs, the encrypted fields remain unreadable without the correct decryption key. For instance, imagine a financial institution managing customer accounts. By encrypting sensitive fields like credit card numbers, even if someone gains unauthorized access to the database, they can't read or misuse the information without the decryption key. Database encryption ensures sensitive data remains protected at all levels. Encryption isn't just a tool, it's a foundation for trust in digital systems. By applying encryption techniques like AES, hashing, salting, and database encryption, we can protect sensitive data and ensure it remains secure, no matter the threat. Every day, sensitive information like passwords and payment details is exchanged over the web. Without strong security protocols, this data could be exposed to attackers, leaving users vulnerable. In this video, we'll demonstrate how TLS and SSL protocols secure data transmissions in a web application. To understand how to secure data transmission, let's start by learning about the key protocols that make it possible, TLS and SSL. Transport Layer Security, or TLS, is a protocol that encrypts data during transmission between a client, for example, your browser or app, and a server. This ensures that data is protected from interception and tampering as it travels across the network, but is only decrypted once it reaches its intended destination. TLS replaced SSL, Secure Socket Layer, an older protocol, but the term SSL is often used to refer to both. Now that you understand what TLS and SSL are, let's start by generating a developer certificate to enable secure communication for your application. To enable HTTPS in your application, we'll use the built-in tools provided by .NET. Open Visual Studio Code and navigate to the terminal. Run the following command: .NET space dev-certs space HTTPS space -- trust. This command generates a developer certificate and adds it to your trusted certificate store. This certificate allows your local development environment to support HTTPS, ensuring all communication is encrypted. To locate the developer certificate, you can use the certificate manager on your system. Use the shortcut Win+R, type cert manager.misc, that's CERTMGR.MSC, and use Enter to open the certificate manager. Once there, navigate to Personal, Open Certificates, and find a certificate with the friendly name ASP.NET Core HTTPS Development Certificate. This is the certificate used to enable HTTPS in your local development environment. With the developer certificate ready, the next step is to configure your ASP.NET Core application to use HTTPS. First, open an existing project or create a new ASP.NET Core application by running .NET new web-o, then give it a name, like Secure App. Then change to the directory that you just created for that project by using cd followed by the name, like Secure App. By default, ASP.NET Core applications automatically use HTTPS when a trusted developer certificate is available. After creating the project, you can adjust the configuration to enforce HTTPS-only communication. Open the launchsettings.json file. This is located in the Properties folder, and modify the HTTPS profile to use only HTTPS. Make sure that the application URL starts with https://. For example, https://localhost:5000. Remember that 5000 is your port, to ensure the application uses HTTPS. Also check that the ASP.NET Core environment is set to development, so the app runs in the correct environment. Next, open the appsettings.json file and configure Kestrel to bind only to the HTTPS endpoint. Ensure the URL in the HTTPS section is set to https://localhost:5000, so Kestrel listens for secure connections on the correct port. Execute the application using the command .NET run. Once it starts, check the console output for a line indicating the HTTPS address, such as now listening on https://localhost:5000. Now that your ASP.NET Core application is configured for HTTPS, let's test the setup. Open a browser and navigate to your application's HTTPS URL. Once there, click on the View Site Information icon, usually located next to the address bar. This will display details about the connection, including a lock icon indicating the connection is secure. You can also view the certificate details, such as its validity and issuer, to confirm that your application is securely communicating over HTTPS. By implementing TLS and SSL protocols, you ensure that your web application protects user data during transmission, building trust and safeguarding against threats in an increasingly digital world.
Whenever you get data from anywhere on the internet, any APIs or other websites, or pass data to an API or other websites, you want to make sure that data is encrypted so people can't snatch it or grab it during transmission. In this lab, we're going to implement encryption and secure transmission protocols in a web application. In step one, we're going to implement HTML encoding. I've got a simple node.js website here in Visual Studio Code. And this website has a simple input form. So you can imagine this is a place where users can enter comments. So we have an input field called user input, a button where they can submit the form, and then a div that displays any output. When the user clicks the button, it runs this process input function. And we're going to do three different things in this function, but for this one, we're going to concentrate on this first section. The first thing we do is grab the input from the user input field up here at the top. We're placing it in the value input. And then the first thing we're going to do is encode any HTML. That means rendering any HTML tags as plain text. By encoding it, the HTML becomes less dangerous. It just becomes a text field rather than actual HTML when we render it to the screen. How we're going to do that is to take that input, and we're going to create a temp div, which is essentially a div element that we're going to hold in memory. And then we're going to assign the input value to that div element, but we're going to use this text content property. By using the text content property, it just renders whatever's in that input to text. So it essentially encodes it for us by using that property. Once it's encoded, then we can also output it, so we can get the output element and also set its text content property to the tempdiv.textContent. The way that we're encoding this is by using that text content property. so we don't have to do any manual encoding. In step 2, we're going to hash and verify passwords. So for that, I'm going to go to this user controller class. And in the user controller class, we have some endpoints. This endpoint is using HTTP post register as the route. In this route, we're going to pass in the user DTO variable, which will contain user information. In this case, name, email, and password. And we're going to check for certain things. We're going to make sure that the name, email, and password is null or it has white space. And we're going to check for those things before we go back and do any more work on it. So as we pass this in, if any of those are true, it's either is null or has white space, we're going to send that back as a bad request and they need to re-enter their data. If that is not true, then we're going to go ahead and encrypt email using the encryption service.encrypt function that we just looked at. And then we're also going to use this bcrypt.net.bcrypt.hash password to hash our password. And that is from an encryption service library that we added earlier. So that bcrypt library will actually do the work of hashing the password for us. So we call the hash password method, passing in the password to get that hashed for us. And then once we go through this process of encrypting the email and hashing the password, now we can create our user object using the encrypted email and hashed password as a part of that object. And then we call users.add to add the user to our database. We have the user object down here and the DTO object and the login object, all as separate classes that we created earlier. So once we've added that user, then we send back the return status for our API call is created, and we send back a message along with that. In step 3, we need to configure our app to use TLS 1.2, which is a secure transmission protocol. So we're going to go into our app settings.json, and we're going to set up this Kestrel object. We call the endpoints as HTTPS. In this case, we're going to use the URL localhost with the port number 5001. Obviously, if this were a real-world app, you would give it a public-facing URL. And then we set the protocols here, and then we're just going to set TLS 1.2 for the protocol for this endpoint. This will allow us to use HTTPS as a protocol and then allow us to use encryption over that secure communication. So TLS 1.2 is a common and standard encryption protocol that's used across the internet. So these are the methods that you can do, very simple, and these are just the starting point for encrypting data. But these are the bare minimum ways that you can encrypt your data so that as it's being passed to and from remote locations, you know that it can remain secure.
Implementing secure coding practices is essential for protecting applications and user data. From input, validation to secure data storage, each step plays a critical role in mitigating vulnerabilities and ensuring the integrity of your application. We began by examining the core principles of secure coding, highlighting essential practices for preventing vulnerabilities and enhancing application security. Next, we explored input validation, focusing on techniques to verify and process user-provided data securely, safeguarding applications from malicious inputs. Then we developed encoding and sanitization techniques, emphasizing their vital role in neutralizing harmful data and preserving application integrity. After that, we concentrated on secure authentication and authorization, exploring strategies to protect user access and safeguard sensitive resources effectively. Finally, we covered secure data storage and transmission methods, identifying strategies to safeguard data at rest and in transit while maintaining its confidentiality and integrity. Mastering secure coding practices is critical to building reliable and resilient web applications. Each technique, from input validation to secure data storage, strengthens your defenses against vulnerabilities and ensures the protection of user data and application integrity. Every line of code has the potential to introduce security vulnerabilities. Microsoft Copilot empowered developers by detecting these risks early, helping you build safer and more reliable applications. In this video, we explain the types of vulnerabilities Microsoft Copilot can detect in code. SQL injection occurs when attackers exploit unsafe user inputs to manipulate your database. For instance, many applications use user inputs, like login credentials, to query a database. If these inputs are properly handled, attackers can insert harmful commands to compromise the data. Imagine you're building a login form and user input directly modifies a database query. Copilot recognizes this pattern and suggests using secure coding practices such as an object relational mapper and input validation to help prevent malicious commands from compromising your database. Cross-site scripting, or XSS attacks, allow attackers to inject harmful scripts into your web pages by exploiting unsanitized user inputs. For example, if users can leave comments on your site without proper validation, an attacker might embed malicious JavaScript. When others visit the page, the script executes in their browsers, potentially stealing sensitive information or manipulating content. Copilot identifies such risks by flagging unsanitized inputs and recommending input validation or encoding techniques to block these threats. Next, let's examine how attackers exploit user sessions with vulnerabilities like cross-site request forgery, or CSRF. Cross-site request forgery, or CSRF, exploits active user sessions to perform unauthorized actions. For example, a malicious website might send a hidden request to transfer funds from a logged-in user's bank account. Without CSRF protections, the server might process this request as legitimate. Copilot can help you implement CSRF protection by suggesting secure handling of user inputs and session management techniques, ensuring your applications handle requests securely. Insecure authentication includes vulnerabilities like hard-coded passwords, storing passwords in plain text, or not using multi-factor authentication. For instance, plain text passwords are easily accessible to attackers, and skipping MFA leaves user accounts more vulnerable to compromise. Copilot helps improve code security by guiding developers away from practices like hard-coding credentials and encourages the use of secure alternatives, such as hashing passwords and implementing multi-factor authentication for added security. By detecting vulnerabilities like SQL injection, XSS, and CSRF, and insecure authentication, Microsoft Copilot acts as a reliable ally for developers. It simplifies the process of writing secure code, giving you the confidence to build applications users can trust.
Using artificial intelligence tools like Microsoft Copilot can help us identify security issues in the code that we're writing. So in this screencast, we're going to describe how Copilot identifies security issues in code. I've got a very simple login script here. It's written in JavaScript. It has some security issues, and you might find code like this on the internet and use it as starter code for an application you're writing. But before we start doing anything with this code, we want to check and see if there are issues that we can fix by using Microsoft Copilot to review it for us and provide fixes. In this screencast, we're just going to look at and ask Copilot to find the vulnerabilities and describe them, and then we can apply them at a later point. To do this, I'm going to just copy this entire code block out. It's pretty simple. There's two different post endpoints, one called login, one called login.db. Again, just to illustrate how Copilot can find some issues here. We're going to take this code, and I'm going to open up Copilot, and then I'm going to ask it to find security issues in this code. Now, I want to focus my questions and ask it to find security issues that are related to storing passwords. I'll give it this prompt. I'm asking Copilot just to describe what the issues are and why they're problems. And I'm telling it I don't really need the updated code at this point. I just want to try to understand where the problems are in this code. And then I just pasted that entire code block into Copilot, so it has the context and can look at what I need it to look at. So now I'll submit the message, and we'll see what Copilot comes back with. So it's given me a number of things here to look at. It's given me 4 items to take a look at. Plain text passwords is the first one. SQL injection vulnerability, there is an issue with how the SQL is being handled. There's a hard-coded password in my code, and there's a lack of input validation. I'm going to put Copilot on this side, and then my code on this side, and we can take a look and see where those issues are. You'll notice plain text passwords. That's up here. We have the password in plain text. Anybody that has access to the code can see the password. That is highly insecure and needs to be fixed. There's a SQL injection vulnerability. The code for the login DB endpoint just creates a SQL query out of the passed in data, the passed in username and password, which can definitely cause problems. People can inject code and then modify the database. Again, the password is hard-coded for both of these. We've got it here as well. The hard-coded password is in the let statement up here, and then it can be used in either one. And then there's a lack of input validation. The code doesn't validate the username and password for malicious code. It just uses it without looking at exactly what's in the data that we're passing in. So Copilot's just told me some things that I can do to improve this code. It hasn't given me the code to fix it because I didn't really want it to do that at this point. I just want to look for what the issues are. The next thing I want to do is check for cross-site scripting or XSS issues. So I'm going to prompt Copilot with that query. So it will go through the code again and look for XSS problems. So it gives me two items. Again, it tells me about the sanitation or validation for the username and password. That was one thing we saw above when it gave a general feedback. And now it's talking about the XSS and login responses. It's how the login information is passed back to the calling code, and it could allow for an attacker to inject malicious scripts. So it's giving me some good information on this code. If I had downloaded this from the internet and wanted to use it, I certainly couldn't use it as is because there's definitely problems here. Finally, I'm going to ask Copilot to look for CSRF or cross-site request forgery issues in this code. It's already given me some indications of where the problems might be, but I'm going to ask it to specifically focus on that problem. So here it's giving me two issues. It tells me that there's no protection mechanism in place. There's nothing in the code itself that protects the application from a request forgery attack, and it can lead to unauthorized actions being carried out on behalf of the user without the user's awareness. And then it says that the login points are vulnerable. There's no mechanism to verify that the request came from a legitimate source. So we would want to improve those endpoints before we actually deploy code like this. It further describes why these are issues and what can happen if we don't fix them. So this code is very basic and needs a lot of improvement before we can roll it out to a live environment and deploy it to users. And we've used Copilot to help us understand what those issues are and how ready this code is for production. And it certainly needs some work before we can push it. You can use Copilot as a code reviewer, and this is super helpful when you're getting code from a source you either don't trust, don't know, or you just want to have validated before you use it.
Every application you create has the potential to be a target for attacks. Identifying and fixing vulnerabilities isn't just about making your software functional. It's about ensuring it's secure and trustworthy for your users. In this video, we'll explain Copilot's approach to suggesting fixes. SQL injection occurs when attackers exploit user inputs, like entering harmful commands in a login form, to access or manipulate a database. To prevent SQL injection, Copilot might suggest using parameterized queries. Parameterized queries are a technique that keeps SQL commands separate from user inputs, ensuring inputs like search terms or login credentials are treated as data, not executable code. This separation prevents attackers from manipulating database queries through malicious inputs. By recommending parameterized queries, Copilot helps you safeguard your database interactions and protect your applications from SQL injection attacks. Once addressing input handling for the database, it's essential to protect the browser from harmful scripts. Cross-site scripting happens when attackers inject harmful scripts into user-generated content, which then is executable in someone else's browser. Copilot suggests escaping untrusted input to block this vulnerability. Escaping assures that any special characters in inputs are displayed as plain text instead of being executed as code. For example, in a product review section, escaping script tags ensures that they display as text rather than running malicious code, safeguarding your users and their data. Now that we've addressed harmful scripts, let's explore how to prevent unauthorized actions with CSRF tokens. Cross-site request forgery, or CSRF, tricks users into performing unintended actions, such as changing account settings or submitting forms without their consent. To counter this, Copilot might suggest adding CSRF tokens, unique identifiers that are tied to a user's sessions. These tokens validate that each request is legitimate and initiated by the intended user. By incorporating CSRF tokens, you ensure that only authorized users can perform secure actions like uploading their profiles or making purchases. Securing individual actions is crucial, but protecting user accounts requires even stronger safeguards. Copilot helps by recommending bcrypt for hashing passwords. Bcrypt converts passwords into secure, unreadable formats, adding layers of resistance to attacks. It also suggests implementing multi-factor authentication, which requires a second verification step, like entering a code sent to a user's phone. Together, hashed passwords and multi-factor authentication provide a robust defense, even if a password is compromised. By addressing vulnerabilities like SQL injection, XSS, CSRF, and weak authentication, you create applications that are both reliable and resilient. Copilot empowers you to apply these fixes seamlessly, making secure coding a natural part of your development process.
When you're working with code from either an unknown source or you want to make sure that the code that you're working with is secure and not subject to vulnerabilities, you can use some AI tools like Microsoft Copilot to help you find and then fix those issues. So in this screencast, we're going to describe how to use Copilot suggested fixes in code. I have a very simple login application here written in JavaScript, and it's got two different endpoints, a login endpoint and a login DB endpoint for illustration purposes. And we're going to ask Copilot to help us fix some of the security vulnerabilities in this code. So I'm going to copy the entire code block out, put it in my clipboard, and then I'm going to start by asking Copilot to fix any issues with SQL injection that's present in this code. All right, so I've written this prompt and I've asked it to actually provide me with fixed code, and I've provided the existing code so that it knows which code to fix. So I'm going to go ahead and send that to Copilot. And it comes back by giving me the code that I would need to fix. Now it's providing me with the entire code base here that I can use. I can either copy and paste this whole thing out, or I can update the one section of the code that I would need. Because I don't quite know what Copilot has changed, I'm going to copy the entire block out and then go back to my code and select everything and then paste that in. So now I've got the updated code here, and Copilot does tell me what it fixed. It says that in this version, the db.query function uses parameterized queries, which is a change from what we had before, where the queries were not parameterized and they could contain malicious code that someone could use to modify the database without the user's understanding. So this ensures that the input is treated as a value and not part of the SQL query itself. So it did help me update and improve that database login function by using these parameterized queries. Now I'm going to ask it to fix any XSS injection issues. We know from analyzing this code that the code is vulnerable to XSS attacks. So I'm going to ask Copilot to help us fix it. So Copilot comes back and tells me, yep, this is very important to fix. And the first thing it's going to have me do is install a library. I won't do that in this screencast, but I would install this library using npm so that we can then use that library. You can see in the code here, we can use that library to help us make this code more secure and solidify the code. You'll notice that what it's doing here in our original code and in the app post login endpoint, we're not sanitizing the user input. So we're just taking whatever is passed in and then we're using that in our login. Here it's using the XSS library to sanitize the input first. So it assigns username variable to the cleaned up or sanitized version of the username variable using that XSS library, and then we can pass that in to our function. It's doing the same thing in the database code as well, just so that we can use that library now to make sure that our code is not subject to that vulnerability. So I'm going to copy that code out and I'll just simply paste that in. Now this is easy to do in this context because the code block is so small. There's not a lot here that I need to worry about. When you have larger code bases, you may want to look more carefully at exactly what Copilot is changing and then just copy and paste those sections out, or hand code it yourself, just see what Copilot has done, and then you can paste it into your code. Now I'm going to ask it to analyze for another vulnerability. This is cross-site request forgery. I can give it a very simple prompt. It knows what a cross-site request forgery is, and it can go through the code and find areas where it's vulnerable and help me improve that code. So you can see it's making quite a bit of changes now. It still includes the code for the XSS vulnerability. It has the sanitizer still in there. It also uses all the database improvements that we made. And now it's just going to add to that a new library called CSRF that allows us to better solidify this code so that cross-site request forgery attacks can't happen. So again, I'm not going to install this library for this screencast, but we would just use that command to install it, and then we would update our code accordingly. So I'm going to do the same thing I did last time. I'm going to copy the code out, select all, and then paste that in. Now, if I were doing this in a real-world environment and everything were set up properly, each time I pasted new code in or took something from Copilot, I would unit test. So I would run the application, make sure it works as expected, and test all that code that Copilot is giving me. Sometimes these AI assistants do make mistakes, so it's important to make sure that you're testing each thing the tool gives back to you so that you can make sure and validate that it works. I'm going to ask it to do one more improvement, and I'm going to ask it to improve the authentication security. So I'm going to ask it to improve authentication by including MFA or multi-factor authentication and hashing of the password so that they're not vulnerable if someone is able to get their hands on the communication between client and server. So here in the first step, it's asking me to install some packages, bcrypt for the password hashing, JSON web token for creating tokens, and node mailer for sending MFA codes and email. So now we have quite a few more libraries that we're adding to our application. So notice that it's including more endpoints here for registering as well as for login with hashing and the MFA included. It has to do this because multi-factor authentication is something that sometimes users need help with. So it's giving me all this extra code so that if a user gets stuck or they need the password reset or whatever, all that code is now provided. It's very high level and very rough at this point, but we can continue to use Copilot to improve all of this new code that it gave us after we've tested it and looked at it in a real world environment. So finally, I'm going to do the same thing. I'm going to copy that code out of Copilot and paste it in here. And now we've got a lot of new things that we can test, and we can make sure that all of these new endpoints work, that we understand them, and that they work as expected. So if a code block doesn't make sense or a code block doesn't work properly, you can copy that code block out or reference it in your chat with Microsoft Copilot, and Copilot can continue to help you improve your code and make it even more secure.
Writing secure code isn't just about avoiding vulnerabilities, it's about building trust and reliability into your applications from the start. With Copilot, integrating security best practices into your workflow becomes effortless. It empowers you to create safer applications, ensuring that secure coding becomes second nature. In this video, we'll describe how Copilot reinforces secure coding practices through recommendations. Let's start with input validation, the first line of defense in ensuring your application only accepts safe and predictable data. Input validation ensures user data follows specific rules to protect your application from harmful or unexpected data. For example, consider a registration form where usernames are limited to letters and numbers. Without validation, attackers could enter harmful scripts or unintended characters that might compromise your system. Copilot simplifies this process by detecting unvalidated input fields and recommending secure validation patterns, such as regular expressions. This ensures your application remains both secure and user-friendly. Validating inputs is crucial, but it's equally important to ensure that any outputs, like user-provided content, are safely displayed. Output encoding transforms potentially dangerous characters and user-generated content into a harmless format, preventing them from being treated as executable code. For instance, imagine a user submitting a comment with special characters like script tags. Encoding ensures these characters display as plain text, rather than executing malicious scripts in your application. Copilot identifies areas where output encoding is necessary and recommends the right techniques for your specific use case, helping protect against vulnerabilities like cross-site scripting. With inputs validated and outputs encoded, the next step is preparing for the unexpected by securely managing errors. Secure error handling ensures your application doesn't expose sensitive details during failures. For example, if a payment fails during checkout, revealing technical details like error 500, database connection failed, could provide attackers with valuable insights into your system. Instead, your app should display a simple user-friendly message like payment failed, please try again. Copilot assists by suggesting try-catch structures that log technical details for developers while presenting safe, professional messages to users. However, it's equally important to avoid overly specific messages such as invalid address for supplied card, as they could provide attackers with hints about how to bypass validation. Instead, use general messages that don't disclose internal logic, such as payment could not be processed. Now that we've explored these secure coding practices, let's see how Copilot makes them an integral part of your workflow. Copilot integrates seamlessly into coding environments like Visual Studio Code to guide you in real time. It flags potential risks, such as missing input validation, output encoding, or error handling, and provides trusted solutions aligned with industry standards like OWASP. By incorporating these best practices directly into its recommendations, Copilot helps ensure your code is both secure and reliable. Secure coding isn't just a task, it's an essential skill for every developer. Copilot helps you master it by embedding best practices into your workflow. With its guidance, you're not just writing code, you're building stronger, safer applications that your users can trust. Web applications are only as secure as the measures taken to protect them. Performing a comprehensive security review is essential to ensure your application can handle evolving threats, safeguard user data, and protect your business from potential breaches. In this video, we'll describe the steps involved in performing a full security review of a web application. A thorough security review begins with identifying potential vulnerabilities in your application's code. Tools like Copilot make this process more efficient by scanning your codebase to detect common issues. For instance, Copilot might flag a SQL injection vulnerability in a login query where user input is embedded directly into a SQL statement, a critical weakness that could allow attackers to manipulate your database. To address these vulnerabilities, Copilot might analyze your code and highlight patterns that deviate from secure practices, providing a clear starting point for remediation. It may suggest techniques such as using parameterized queries, stored procedures, or input validation to mitigate tasks. By implementing these recommendations, you can significantly strengthen your application security and protect it against potential threats. Once vulnerabilities are identified, the next step is to address them by implementing secure coding practices. Secure coding practices such as input validation, output encoding, and proper authentication ensure your application meets industry security standards and minimizes risks. For example, input validation ensures that user-provided data adheres to specific rules. Imagine a registration form where usernames are restricted to letters and numbers. Without validation, an attacker might submit a username containing harmful scripts, potentially exploiting your application. By enforcing proper input validation, such as rejecting invalid characters, you can safeguard your application from malicious inputs. Similarly, output encoding transforms potentially dangerous characters and user-generated content into harmless text. For instance, if a user submits a comment containing a script tag, encoding ensures these tags are displayed as plain text rather than executing harmful code in the browser, protecting your users from vulnerabilities like cross-site scripting. Copilot enhances this process by identifying areas where secure practices are missing and suggesting patterns to address them effectively, helping you implement robust fixes aligned with industry standards. Security measures should strengthen your application without negatively impacting performance. After implementing fixes, it's important to test and optimize your code to maintain both security and efficiency. For example, encrypting passwords can increase the time it takes to query the database, especially with a large data set. Adding an index to relevant database fields helps optimize query performance without compromising the strength of encryption. Copilot assists by identifying these performance bottlenecks and recommending solutions to ensure your application remains both secure and efficient. Security doesn't end after applying fixes. It's an ongoing process that requires continuous vigilance, and monitoring. Implement automated tools and workflows to proactively detect new vulnerabilities as your application evolves. For instance, Copilot can assist you in recognizing patterns that may indicate potential security risks in your codebase. Additionally, it can suggest best practices for maintaining up-to-date dependencies, helping you address vulnerabilities before they can be exploited. By establishing a robust system for regular checks, you ensure your application stays secure over time, consistently adapting to emerging threats and maintaining user trust. Security is a continuous journey, not a one-time task. By following these steps, analyzing the codebase, applying secure coding practices, optimizing performance, and preparing for continuous monitoring, you're building a strong foundation for resilient and efficient applications. With Copilot's guidance, secure coding becomes an integrated part of your workflow, empowering you to create applications that are ready for the challenges of tomorrow.
Once you've developed your code, it can be really important and helpful to do a thorough security review, particularly if you're using APIs, developing APIs, or doing anything that requires or uses sensitive data. So in this screencast, we're going to demonstrate how to use Copilot to conduct a complete security review. You can use tools like Copilot, any generative AI tool, to look at your code and review it and provide feedback. I have a simple node.js application here in an app.js file, and I'm going to have Copilot review this with me. It's got some errors in it already. We've got built in the errors just to illustrate how we can use Copilot for this purpose. So I'm going to actually pin this to the side of the screen so that we can have Copilot up next to us. So I've got Copilot in my right pane window and then the code in this other pane. I'm going to ask Copilot a very general query. I'm going to ask it just to do a thorough security review. And I'm going to paste the code right into Copilot. If you have Copilot integrated into Visual Studio Code, you don't need to paste it. You can just have it do it right in line. But for the purposes of this screencast, I'm going to paste in the code because it's so simple and there's only one file. So I'm going to copy the entire code out and I'm going to paste that into Copilot. So now it has all the code and I'm going to ask it to review it. Copilot quickly comes back and says, I see a few vulnerabilities in your code, and it offers suggestions on how to fix that. It categorizes them. So the first one is SQL injection vulnerability, and it tells me that my code is subject to an injection attack. And then it provides the code for how to fix that attack. The next vulnerability it talks about is hard-coded database credentials. We have the password and the username built into the code base, and it's suggesting that we don't do that. We take that out and pass those in as variables, so then it's providing the code so that we can do that. It also says that there's no error handling, so we should implement proper error handling to avoid exposing sensitive details. Each time Copilot gives me the fix for one section, it's including all the code. So I can essentially take this entire block by copying it out of Copilot and pasting it right into my application. Many times Copilot will give you just a function or a portion of code that you'll need to look through and before you do any pasting. It's also a very good idea to review the suggestions that Copilot's giving you to make sure they make sense. I could ask Copilot here to comment each portion of code so that we know what it's doing, and that will provide some better visibility into what Copilot has actually done and help you later as you want to review the code or make any changes yourself. The next thing I'm going to have Copilot do is provide a summary of the vulnerabilities. It's like a report. It did this as it was going through in each section, but I'm just going to ask it to summarize what it did for me so that I can have a review in one place, and then I can go ahead and review those changes as I'm putting them into my code. I'm next going to ask it how I can create an automatic security check for this application. So now that the app is done, I've got the fixes in place, I want to make sure that no new vulnerabilities crop up. So I want to ask Copilot to provide me with the ability to do an automated security check for the application. It's giving me, again, suggestions that I can take in order. I can reject whatever I need to here. Again, we're working with Copilot on this. I'm not going to just take all the suggestions as they are. And Copilot is giving me a bunch of options in many cases for how to implement some of these checks. So I want to make sure I go through this carefully. First, it says choose continuous integration, continuous deployment platform, GitHub Actions, GitLab. Those are some options. Jenkins is a popular one. So you can use these CI/CD platform options. Then it says set up a CD pipeline and gives me some code for how to set up that workflow. I can integrate security scanning tools. Some of these are built right into VS Code, so I can have the security scanning tools happen while I'm actually coding. Others are not. You'll have to run them as a separate process. It also recommends that I run tests and review reports as these tools are doing their job. So Copilot's giving me some options here for better ways that I can ensure I'm doing a thorough job in preparing my application to be more secure. And that allows us to not only make sure that the code that we've written is more secure, but that we have an ongoing process for building in security into our application.
AI has transformed security by delivering unmatched speed and precision in threat detection. But its full potential emerges only when combined with human expertise, which helps overcome its limitations and make it even more effective. In this video, we'll describe the strengths and limitations of AI-driven security recommendations. Let's start with AI strengths: its speed, efficiency, and ability to identify patterns. These are the qualities that make it a vital tool for security. For example, AI can instantly analyze millions of login attempts to detect unusual activity, such as repeated failed logins on one account. It can then block the sources before the situation escalates, providing a response that humans simply can't achieve at scale. AI excels at identifying patterns and trends that might go unnoticed by humans. Imagine multiple users accessing the same data from a suspicious location. A single instance might seem normal, but AI connects the dots to uncover a possible coordinated attack. This ability to spot hidden patterns sets AI apart. Despite its strengths, AI has limitations. It relies heavily on patterns and rules, which means it doesn't always understand the context behind an action. For instance, an employee logging in from another country during a business trip might trigger a security alert. While AI flags this as suspicious, it lacks the broader knowledge to confirm whether it's legitimate. AI sometimes misinterprets routine activity as security threats. For example, a large data transfer during a scheduled system update might trigger a security alert. While the AI flags this as a potential breach, a human analyst can step in to confirm it's just normal maintenance, ensuring operations aren't unnecessarily disrupted. Because AI struggles with context and nuance, manual reviews are critical for bridging these gaps. Pairing AI with human expertise creates a stronger, more adaptable security system. For example, if AI flags a login from an unfamiliar device, a human analyst can step in to check if it's a real threat or just a traveling employee avoiding unnecessary interruptions. Over time, human feedback helps AI improve. When analysts mark similar flagged events as safe, AI learns to stop flagging them, making it more accurate by working together. AI and human experts create a stronger, more reliable security system. AI-driven security systems are fast, efficient, and powerful, but their true strength lies in how they work alongside human expertise. By understanding this balance, we can build security systems that are not only intelligent, but also adapt to any challenges.
When building an app, you always want to keep security in mind. And modern AI tools like Microsoft Copilot can help you improve your app's security by offering suggestions and improvements. Whatever AI tool you end up going with, it's always good to do a manual review as well, because sometimes the AI tools may not be able to give you everything that you need because they misunderstand intent or they don't have the full context for your application. There's a number of reasons why an AI tool like Copilot may not give you a thorough or holistic response. So you not only want to review the feedback that Copilot's giving you, but also do a manual review of your code. So in this screencast, we're going to compare AI reviews to manual reviews. And we'll look at the difference between how the tool works and how your own manual review will work. I have a simple Node.js application here with some built-in security flaws. And I'm going to ask Copilot to help me review this, and then I'm going to do a manual review to see if I catch anything other than what Copilot provided. So I'm going to pin this to the side and then put Copilot up here. I'm going to ask Copilot to give me just a general security review of this code, and then I'll see what fixes it suggests, and then I'll do my own kind of manual review of it. So I'll paste in the prompt, and then I'm going to paste in my code. It's small and short, so I can just paste in the whole thing here. And I'm going to ask it to go through the entire code and give me some fixes. So it categorizes the fixes it provides. So the first is a SQL injection vulnerability, and it tells me where this is and what I can do to fix it. That's something that we would hopefully catch even in a manual review. We have passwords in plain text here, which is something that we want to avoid from a security perspective. So that's something we can definitely fix by using a hashing algorithm, and Copilot provides the way that we can do that. It provides the code so we can update that. It tells me that I have hard-coded credentials, and there's definitely a problem there. I have the credentials built right into the code rather than passing them in. And it says it's throwing errors directly, which can reveal sensitive information. So that's a fourth error that it calls out. So it gives me 4 general categories, and these are good things to call out, and it provides the code that I can use to fix them. Now I'm going to go through and manually review the code that I have just to make sure there's nothing else missing here that I might want to check on. One thing I noticed from this code is that there's no logging, and Copilot did not suggest that. When you're thinking about security issues, keeping a log of what's happening in your code, obviously a private secure log, that you can go back and review in case someone has attempted to hack your code or someone has attempted to gain access without your knowledge. Keeping a log or a record of who has tried to use your API, for example, in this case, we have a login route in our API. Keeping a log can help you find errors and issues and analyzing that log on a regular basis. So we would want to add that. We would want to add some logging to our API to make sure that no one's trying to gain access. Another quick thing I notice here too is that there's no rate limiting for our API. So one potential security issue is someone could try to hack the website or the API by flooding it with requests all at one time, which can take down the API or make it inaccessible to valid users, and that could present a security problem. So we would want to limit how many requests can be made in a certain period of time, and we would want to build that into this code as well, particularly for this login route. Copilot did not suggest that as an option either. So just in that manual review, I caught a couple of things that Copilot did not catch. These are things that I probably would want to add before I ever ship this API to the public. I could go back to Copilot and say that I wanted to add those 2 features, logging and rate limiting, and Copilot would then provide the code or provide assistance in helping me build that into my code base. So while Copilot is a great tool and super helpful, this general prompt here just wasn't enough detail for Copilot to give me everything that I needed. So I could be more specific in my prompt. I can use terms like best practices. What are some best practices I could use? Do a thorough scan of this code and provide every possible way that I could improve it. That's another prompt, which could give you a lot more detail than you want at the beginning. But the general prompt didn't really give me everything that I would want to secure this code, and a manual review did, and then I can go back to Copilot and work with Copilot based on that manual review and improve my code even further.
Leveraging Microsoft Copilot can transform how security vulnerabilities are identified and resolved. By applying its AI-driven insights, you gain valuable experience in enhancing application resilience and conducting comprehensive security reviews, ensuring robust protection against modern threats. We began by exploring how Microsoft Copilot identifies potential security vulnerabilities in code, providing insights into risks that could compromise application security. Next, we focused on using Microsoft Copilot to resolve identified issues, learning how AI-driven suggestions streamlined the process of fixing vulnerabilities effectively. Then, we applied secure coding practices with the help of Copilot, discovering how it assisted in implementing strategies that enhanced applications' overall resilience. And after that, we conducted a comprehensive security review, leveraging Copilot to assess and enhance the security of a web application from end to end. Finally, we evaluated the impact of AI-driven security practices, analyzing their effectiveness and understanding how they fit into a broader security strategy. Effectively leveraging Microsoft Copilot for security practices is essential for building robust, resilient web applications. Its AI-driven insights enable you to identify vulnerabilities, implement effective solutions, and conduct thorough security reviews, ensuring your applications are protected against modern threats.
Behind every smooth online shopping experience is a well-structured system that processes products, manages orders, and ensures data is stored correctly. Understanding how business logic works is essential for building efficient and scalable e-commerce applications. In this video, we'll explain key concepts related to developing business logic for an e-commerce web application. Before we build business logic, we need a foundation in C#, the language that powers our application. Let's begin with some key concepts. C# is a programming language used to create business logic. It allows developers to define how data is handled and actions are performed. There are three essential concepts in C#. Variables store data such as keeping track of a product's price, decimal price equals $49.99. Methods define actions. A method like apply discount decimal percent can adjust a product's price when a sale is active. Classes group related data in methods. In an e-commerce system, a product class could store name, price, and stock level of an item, along with a method to update inventory. Now that we understand basic C# concepts, we can explore how Object-Oriented Program, OOP, structures business logic in a scalable way. OOP organizes code using classes, or blueprints, and objects, real-world instances of those classes. It structures data and actions in an organized way, making it easier to manage and expand an application. A customer making a purchase is a great example. The customer class could store details like their name and email, while including a place order method that finalizes their order and updates stock levels. Without OOP, managing these interactions will require a more complex and repetitive approach. Now that we know how OOP helps structure code, we need to create classes that represent real-world business concepts. In an e-commerce system, every product, user, and order needs a class to organize its details and functions. Before writing business logic, let's see how a class is structured in C#. In C#, a class is created using the class keyword, followed by properties and methods inside curly braces. A user profile system is a good example. We can define a user class with properties like username and email, along with methods for updating passwords or retrieving order history. With this structure, managing user data becomes straightforward. One of the key components of an e-commerce site is its products. Let's create a product class to store and manage product data. A product class represents an item in the online store. It includes attributes like name, price, and stock quantity, and behaviors like applying discounts and updating stock. Consider an online clothing store where prices decrease during sales. A product class can have an apply discount method that updates the price dynamically, ensuring customers always see the correct sale price. Now that we can define products, we need a way for customers to select and purchase them. That's where the cart class comes in. A cart class manages selected products, calculates totals, and interacts with the database. The cart class must store products, calculate the total price, and allow customers to remove items. When a customer adds items to their cart, the system needs to calculate their total dynamically. The cart class ensures that if a user removes an item, the price updates immediately, just like in a real online store. A shopping cart needs to store data so items are not lost when a user refreshes or logs out. This is done using a database. A database stores information so it can be accessed later. In e-commerce, databases store products, orders, and customers. A database consists of tables, which store data in rows and columns, primary keys, which are unique identifiers for records, and SQL queries. These are commands to add, retrieve, or delete data. An online bookstore, for instance, stores book details in a products table. When a customer searches for a title, a SQL query retrieves matching records instantly. Storing data in MySQL is only useful if our C# application can access it. To make this connection, we use database libraries like ADO.NET or Entity Framework, which allows C# to send SQL queries and retrieve results. Let's see how this works before integrating MySQL into our project. MySQL helps store shopping cart data so users don't lose their cart items. This process involves first creating a database table for cart items, then writing C# methods to save, update, and delete cart data, and finally using SQL queries to retrieve saved carts. Picture a customer adding a laptop to their cart. When they log in later, this item is still there. That's because when they added it, an insert SQL command stored it in cart_items. The foundation of any e-commerce application lies in how well its business logic is designed. By structuring code with C#, OOP, and databases, developers create applications that handle transactions efficiently and provide seamless user experiences. A well-structured front-end application isn't just about writing code. It's about building reusable components, managing interactions, and ensuring data flows efficiently. Understanding these core concepts allows developers to create scalable and maintainable Blazor applications that function smoothly as they grow. In this video, we'll explain key concepts related to building and managing Blazor components in a front-end web application. At the heart of every Blazor application are components. These building blocks shape the user interface and define how different parts of the application interact. Let's start by understanding what a Blazor component is. A Blazor component is a reusable, self-contained piece of code that manages the user interface, UI, logic, and state for specific parts of the app. Blazor components help structure applications by breaking them into smaller reusable parts. Each component manages its own UI and logic, improving maintainability. Imagine a navigation menu appearing across multiple pages. Instead of writing it repeatedly, a navmenu.razor component can be created once and used throughout the application. This simplifies development and keeps the code organized. Components become even more powerful when they can exchange data. That's where component parameters come in. A component parameter is a property that allows a Blazor component to receive data, usually from a parent component. Parameters make components more flexible by allowing them to display different content dynamically. Imagine an online store showing product listings. Instead of creating a separate component for each product, a product card.razor component can receive a product parameter from the parent component. This way, the same component can be used for multiple products with unique details displayed for each one. Passing data between components is useful, but applications must also handle user interactions. Let's examine how Blazor manages events. Event-driven development is a programming approach where user actions trigger events that execute specific programming code. Blazor enables seamless interaction by binding user actions to methods. Take a simple counter component. Each time a user clicks a button, the number on the screen should increase. In Blazor, you can bind the button's onClick event to an increment count method, which updates the value. This approach makes applications interactive without writing complex JavaScript. Handling user interactions is essential to a responsive app. Blazor apps also need to persist data beyond a single interaction. Up to this point, our app only updates values inside one component. But what if a user adds an item to their cart and expects to see it on another page? The application needs a way to store and share data across components. That's where state management comes in. State management is the way an application keeps track of the current state or data across different parts of the system, ensuring a consistent user experience. In a Blazor application, state refers to data that needs to be tracked and updated as users interact with the app. For example, a shopping cart should retain its contents across different pages. Blazor supports this through dependency injection, where a shopping cart service manages cart data. This ensures consistency without unnecessary reloading. Using components, Blazor provides powerful ways to enable interactions and manage data. However, sometimes even well-structured applications don't behave as expected. A component might re-render too often, slowing things down,
or data might not update correctly due to a state management issue. Finding and fixing these problems can be time-consuming, but AI-powered tools like Microsoft Copilot can help detect and solve issues faster. Copilot enhances development by identifying inefficiencies and suggesting improvements. If a component keeps reloading even when known changes occur, Copilot can detect the issue and suggest ways to prevent the app from rendering the content unnecessarily. It also helps catch errors before they become problems, making development smoother and faster. Imagine you're building an e-commerce application using Blazor. Here's how these concepts work together. The product card.razor component structures how each product appears. The product parameter allows the component to display different products dynamically. Clicking Add to Cart triggers an on-click event, updating the shopping cart. A shopping cart service manages cart state, ensuring items persist across pages. And then Copilot optimizes performance by reducing unnecessary re-renders. By applying these concepts, you can develop a scalable and interactive web application with a strong architectural foundation. Modern web applications rely on well-structured components, state management, and optimization. Mastering these Blazor concepts allows developers to build applications that efficiently handle user interactions and adapt as requirements evolve. A well-designed interface does more than look good. It creates a seamless, accessible experience for every user on any device. Whether adjusting layouts for different screen sizes or improving accessibility for individuals with disabilities, strong user interface and user experience design ensures that web applications are intuitive, inclusive, and user-friendly. In this video, we'll explain key concepts related to enhancing the user interface or user experience through responsive design and accessibility in front-end web applications. Creating an effective user experience begins with understanding the core principles of user interface user experience, or UI/UX design. These principles shape how users interact with a website, ensuring that it is visually appealing, easy to navigate, and accessible. UI/UX design is the process of creating digital experiences that prioritize usability, accessibility, and aesthetics. A visually balanced layout ensures elements are evenly arranged, creating a sense of stability. When sections of a web page have equal spacing, the design feels structured rather than cluttered. Strong contrast between text and background makes content easier to understand, and white text on a navy blue background improves readability. Organizing content by importance guides users naturally. A news website that displays headlines in larger, bolder text, for example, allows readers to quickly identify key stories. A design that works for everyone ensures inclusivity. A login form that allows users to navigate using only a keyboard provides equal access for those who rely on assistive technology. Now that we understand UI/UX principles, applying them visually is essential. CSS styling controls how web pages look and feel, ensuring a well-structured layout. CSS styling is a language that manages layout, colors, fonts, and spacing to enhance web design. Typography influences readability by ensuring that fonts and spacing enhance legibility. A blog that uses a sans serif font with adequate spacing between lines provides a more comfortable reading experience than one where text is packed too closely together. Layout plays a crucial role in organizing content for better usability. When an online store uses CSS Grid to structure its product display, typography and spacing contribute to a seamless browsing experience. Media queries further enhance responsiveness by adjusting the layout for different screen sizes, ensuring the design remains functional and visually appealing across devices. Spacing improves readability and usability by creating visual separation between elements. A sign-up form with adequate spacing between input fields is easier to use than one where elements are placed too close together. Accessibility ensures usability, but manually checking every UI element for best practices can be time-consuming. But this is where AI tools like Microsoft Copilot can help. Microsoft Copilot is an AI-powered tool that helps optimize UI layouts, refine styles, and ensure accessibility compliance. Copilot enhances design by helping developers refine UI styles, suggesting better font sizes, spacing, and colors to improve readability. It helps improve layouts by suggesting adjustments to alignment for better structure and flow. Additionally, it ensures the website is accessible by identifying areas of the site that have low contrast and missing attributes that enhance screen reader support, providing clear navigation and interaction. Now that we've explored these key concepts, let's analyze how they come together in a real-world project. A company preparing to launch a new product needed a well-designed landing page that was visually appealing, accessible, and adaptable to different devices. By applying UI/UX principles, CSS styling, and responsive design, they aimed to create an intuitive user experience. Using Copilot, they received immediate recommendations for typography, spacing, color contrast, and layout improvements, ensuring accessibility compliance. These AI-assisted enhancements streamlined the design process, allowing them to launch ahead of schedule with a well-structured, user-friendly website. By combining UI/UX principles, responsive design, accessibility practices, and AI-powered enhancements, developers create web applications that are not only visually appealing, but also intuitive and inclusive. Mastering these techniques ensures that every user, regardless of device or ability, can interact with digital experiences effortlessly. Every time a user interacts with a web application, submitting a form, logging in, or posting a comment, attackers search for weaknesses to exploit. Weak security practices leave applications vulnerable to exploits that can compromise data, disrupt services, and damage trust. Secure coding practices are essential for building applications that protect both users and systems from common threats. In this video, we'll explain key concepts related to implementing secure coding practices in a front-end web application. A major source of security vulnerabilities comes from user input. Let's begin by understanding how input validation and sanitization helps prevent attacks. Input validation ensures user input follows expected rules before processing. Data sanitization removes or modifies harmful content to prevent attacks. Attackers often target input fields because they allow direct user interaction with an application. If an application doesn't check or clean up inputs, attackers can insert harmful code. These techniques help stop SQL injection and XSS, two of the most common web vulnerabilities. SQL injection is when a login form doesn't validate inputs. An attacker could enter or 1 equals 1 as a username, tricking the system into logging them in without a password. Without proper validation, the database processes this as a valid query, allowing unauthorized access. In XSS or cross-site scripting, a comment box without sanitization could let an attacker inject script alert hacked script, which would execute as soon as another user views the page. This can be used to steal session data, redirect users, or modify site content. Validation prevents harmful inputs from reaching the system, while sanitization ensures safe handling of user data. While input validation and sanitization help prevent attacks, secure coding practices provide additional protection to keep applications safe. Attackers often try to guess passwords using automated tools. A strong password policy that requires long, complex passwords makes brute force attacks much harder. Unsecured session and unencrypted connections can expose sensitive data. Implementing secure session tokens and enforcing HTTPS helps protect users from data theft. Bugs and vulnerabilities often go unnoticed until they're exploited. Running security scans before deployment helps detect these issues before attackers can take advantage of them. Secure coding keeps applications protected, but without authentication, attackers could still gain unauthorized access. Let's explore how authentication works. Authentication verifies user identity before allowing access. Secure authentication ensures that only authorized users can log in. A secure login system should enforce strong password policies to prevent guessing attacks. Multi-factor authentication, or MFA, adds an extra layer of security, making unauthorized logins much harder. ASP.NET Identity helps implement authentication in web apps by managing users, enforcing password policies, and handling security roles. Developers can use it to create a secure authentication system without writing everything from scratch. Authentication secures user access, but how do we ensure that applications remain free of vulnerabilities over time? That's where security testing and AI tools can help. Many applications keep users logged in by using tokens instead of asking for credentials every time. These tokens must be securely stored and expire after a set time to prevent unauthorized use. Traditionally, developers perform manual security testing to find vulnerabilities, but this can be time-consuming and difficult to scale across large applications. Security teams often use automated tools to speed up this process. AI tools like Microsoft Copilot can make security testing even more efficient by detecting issues in real time. Microsoft Copilot assists developers by detecting vulnerabilities and suggesting secure coding improvements. Copilot identifies security flaws like SQL injection or XSS and suggests secure fixes, reducing manual security testing efforts. AI-powered tools like Copilot improve security testing by making it more accurate and efficient. We'll explore how to use them in later lessons. Now that we've covered essential security techniques, let's examine how they work together in a real-world scenario. Imagine building a user registration form for an e-commerce website. How do we secure it? First, we validate user inputs. If someone enters an email like user@example.com, proper validation would prevent it from being accepted. Strong password requirements ensure that weak passwords aren't allowed. Next, we sanitize inputs. If a user tries to insert malicious JavaScript into the name field, sanitization will strip or encode dangerous characters to prevent execution. Then we implement authentication. A login system should verify users with a secure password policy, and MFA should be enabled for additional security. Finally, we'll apply best practices. Using HTTPS ensures that all user credentials and session data remain encrypted, while strong session management prevents unauthorized access. With all these layers of security working together, they create a strong defense against common attacks. By applying these security techniques, we can prevent many common threats. Secure coding isn't just about preventing attacks, it's about creating a foundation for a safe and reliable application. When security is built into development from the start, applications remain resilient, protecting both users and their data from evolving threats. Completing a front-end web application isn't just about writing code. It's about ensuring the app functions smoothly, remembers user data, and is polished enough to showcase. In this video, we'll explain key concepts related to integrating state management and finalizing a front-end web application. To create a reliable and professional project, managing how data is stored and maintained across user interactions is essential. State allows applications to track user activity. Without it, everything resets when the page reloads, disrupting usability and causing frustration. State management is the way an application keeps track of the current state or data across different parts of the system, ensuring a consistent user experience. This creates a seamless experience by retaining user preferences, shopping cart items, and form inputs, preventing unnecessary resets. Tracking state within an application allows data to persist during a session, but once a user refreshes or leaves, that data is lost. To maintain state across sessions, storage solutions are essential. Local storage is a way to persist data even after closing the browser, ensuring settings like dark mode or saved preferences remain available. Session storage, on the other hand, temporarily holds data while the page is open, allowing it to persist through refreshes, but clearing it once the browser or tab is closed. For example, when a user adds items to an online shopping cart and returns later to find them still there, that's local storage in action. Without it, refreshing the page or revisiting the site would reset the cart, leading to a frustrating experience. Similarly, if a user filling out a form and refreshes the form by accident, session storage ensures that the input data isn't lost while the page remains open. Next, debugging helps identify and resolve errors, making sure everything works as expected. Debugging is the process of finding and fixing issues in code to maintain proper functionality. Developers can approach this manually or use AI-assisted tools to streamline the process. Manual debugging involves inspecting issues by logging values, setting breakpoints in the browser, and analyzing error messages to pinpoint the source of the problem. AI-assisted debugging, on the other hand, using tools like Copilot, speeds up this process by analyzing code and suggesting fixes or optimizations automatically. For example, if clicking a button does nothing, checking the console log might reveal that the event listener isn't running. Instead of guessing, this debugging activity directs you to the exact point where the issue needs to be fixed. Even after debugging, an application isn't truly complete until it has been thoroughly tested and optimized for performance. Testing involves interacting with buttons, forms, and the navigation elements to confirm that every feature works as expected. Testing ensures that all components function correctly, while optimization enhances speed, usability, and accessibility. Optimization further improves performance by minifying code, compressing large images, and removing unnecessary elements. Tools like Lighthouse help you evaluate accessibility, ensuring the application remains usable for all users. For example, when testing an e-commerce site, the Add to Cart button might work, but the Checkout button could be unresponsive. Identifying and fixing these issues before users encounter them prevents frustration. Additionally, optimizing performance by compressing large images speeds up the site, improving both user experience and engagement. Once a project is tested and optimized, presenting it professionally makes a difference. A portfolio-ready project is a structured, documented, and visually polished application designed for professional presentation. A well-organized project structure means it's easier for others to understand and navigate. Storing assets in designated folders, keeping components modular, and maintaining clean code reflects strong development practices. Something as simple as a README file acts as an instruction manual, explaining what the project does, how to use it, and set up steps. This ensures anyone exploring the project can easily run it. Polishing the UI further enhances the presentation. A clean, responsive design improves user experience and demonstrates attention to detail. But a portfolio isn't just about code, it's about showcasing a developer's ability to build, optimize, and present functional applications. Let's bring all this together with a real-world example. Imagine you're building a task manager where users can add, edit, and delete tasks. To finalize this project, you need to store tasks across sessions using local storage, debug issues by checking console logs and using developer tools, and optimizing performance with Copilot's suggestions. Testing ensures everything runs smoothly, while deploying the project online makes it accessible to others. A fully polished, portfolio-ready project isn't just functional. It's well-structured, optimized, and built for real-world use. A front-end project isn't truly complete until it is tested and optimized and structured for real-world use. The ability to manage state, debug efficiently, and present a polished final product transforms a simple coding project into a professional application. Congratulations on completing the Web Application Security course. You've built a strong foundation in identifying vulnerabilities, implementing secure coding practices, and leveraging Microsoft Copilot to enhance application security. We began by examining common web application vulnerabilities, breaking down how attacks like SQL injection, cross-site scripting, XSS, and cross-site request forgery, CSRF, exploited application weaknesses and the real-world consequences that caused. Next, we focused on secure coding practices, exploring techniques for input validation, output encoding, and data protection. We did this to minimize security risks. We also learned how strong authentication and authorization mechanisms helped safeguard user data. Then we integrated Microsoft Copilot into security workflows, using its AI-powered capabilities to detect vulnerabilities, suggest fixes, and apply secure coding principles to strengthen web applications. Finally, you put your skills to the test in a Capstone project, applying everything you had learned to identify, mitigate, and prevent security threats in a real-world web application scenario. By applying these skills, you're now equipped to protect web applications against common threats
and contribute to a more secure digital environment. Keep refining your expertise, stay updated on evolving security challenges, and continue building secure, resilient applications. Great job. Congratulations on reaching the end of the Microsoft Front-End Developer Professional Certificate Program. Throughout this journey, you've built a strong foundation in front-end development, mastering key programming concepts, frameworks, and industry tools. From writing efficient code and designing interactive web applications to implementing security best practices, you've gained the technical and problem-solving skills essential for success in front-end development. We began by introducing the core principles of front-end development, covering essential coding practices, project planning techniques, and logical problem solving. You learned how to break down complex problems into structured algorithms and flowcharts, setting the foundation for writing efficient code. Next, we explored C# programming, where you got hands-on with the .NET environment in Visual Studio Code. You wrote your first C# programs using variables, loops, and methods, while exploring object-oriented principles like classes and inheritance. Along the way, you practiced debugging and optimizing code with Microsoft Copilot to improve efficiency. Then we shifted our focus to web development, starting with the fundamentals of HTML, CSS, and JavaScript. You explored responsive design principles, asynchronous JavaScript, and version control with Git. As you progressed, you integrated Microsoft Copilot into your workflow to accelerate coding and enhance your web projects. After that, we worked with Blazor to build interactive front-end applications. You explored how Blazor components handle data binding, navigation, and state management, gaining experience in running and debugging Blazor applications. By the end, you developed a Blazor project while leveraging Microsoft Copilot to streamline development. Finally, we explored UI/UX design principles, focusing on wireframing, prototyping, and responsive design techniques. You applied user-centric design practices to create intuitive interfaces while optimizing CSS and layouts with Microsoft Copilot. You refined your designs through practical workflows to enhance user experiences across devices. We concluded with an in-depth exploration of web application security, addressing common vulnerabilities and secure coding principles. You examined threats like SQL injection, cross-site scripting, XSS, and cross-site request forgery, CSRF, learning to mitigate risks through input validation, authentication best practices, and secure data handling. By completing this program, you've equipped yourself with the knowledge and hands-on experience needed to develop dynamic, responsive, and secure web applications. You've worked with C#, Blazor, and modern front-end technologies, applying UI/UX principles and security techniques to real-world projects. With these skills, you're now ready to take on professional front-end development roles, contribute to innovative projects, and continue growing in this ever-evolving field. Congratulations on this achievement, and best of luck in your next steps.